Hi, Professor Ahmed Kish.
Hi.
Morning.
Good morning.
Finally, you have joined. I think
Yeah.
some problems in joining the link.
Yeah. How I can share the screen?
Okay. That I'll tell you. No problem.
Okay.
Okay. And before commencing the session, I must guide you how to share that one. On the bottom, let me stop my on screen.
Okay.
On bottom right side, there is one icon, present now.
Oh, present now. Okay.
Okay, you just click on that one and select entire screen. Then it will come your laptop screen or desktop screen in the picture. Then you click the presentation and go into slideshow mode, and automatically will come.
Okay. Share. I say share.
Yeah, share.
Because I only see. I don't see the back of my screen.
Okay, you just open
okay,
that.
I have it now.
Okay.
This one. Share.
Yeah.
Okay. Still, you're presenting to everyone. Okay, where it doesn't show my file.
You need to select the window after clicking on share. Then you need to select. You stop presenting and do it again.
Okay.
You stop
presenting. Say you are presenting. So I say stop.
Yeah.
Presenting.
Yeah.
Presenting now again.
Now you click on that one, present now.
Okay. And say your entire screen.
Yeah. Or that particular window where PPT presentation is there. You may select either entire screen or that particular window. That is up to you. That presentation is open, or
should I click on the file?
Not file. I am doing the process from my side.
Share. I say share.
Yeah.
But it is disabled. It said cancel.
Okay, then you can
to connect your screen with Meet. Choose what you like to share. Share what you like to share.
No. This type of message should not appear because I think there is some problem. You can disconnect that one. I am repeating the process from my side. Okay. Stop that one and then click on present now. Dr. Soni Kiran.
Sir, can I say something?
Yeah. Sure.
Professor Kisak first need to open the presentation in his own laptop.
Oh, okay.
Yes, sir.
Where is your presentation?
First you open your PPT or PDF any file.
I'm opening the PowerPoint now.
Okay.
It is opening because it's a big file. It is taking some time. Now it is opened. Yeah. So now I can share.
Now you can go to the right hand side bottom, that is present now.
Present now, and I said entire screen or
Yeah.
a window.
Entire screen.
Okay. It gives me the same message: share your entire screen. Chrome wants to share the contents of your screen with Meet. Google, choose what you would like to share.
No, I think it should not. That link was forwarded to your Gmail ID also. I think you should open that Gmail ID and directly you can connect from that. Might be you are doing the process through your official email ID.
I don't know. I just clicked on the link, as you said, refresh.
Okay. While you are going for present now, are you clicking your entire screen? Present entire screen?
Yes, I did that. Now, here.
Now you just need to select and share option.
I shared the entire screen, and it showed me the screen where I see everything, but not my presentation, because my presentation is hidden in the back. Yeah, here, like, okay, I choose this one now. Share.
Yes, you can click share.
Yes.
Yeah.
Yes. And now you can choose your PPT file or presentation.
Yes.
Do you see anything?
Yes, it is visible.
Is the blue screen?
Yes, visible.
Yes.
Oh, okay. So that means I can make it
Yes.
full screen?
Yes.
Okay.
Sir, on bottom side, there is one icon on your screen. You please hide that icon. Not stop, hide that icon.
Okay.
Yeah. Okay, now it is fine. Okay. Let me start the session. Good evening, good afternoon, as well as good morning to all. Welcome you all again to the second day of 1 week long ongoing Indo-Canada Spark course on Dielectric Resonator and its applications, DRA-2020, organized by National Institute of Technology, Silchar, India, in association with Delhi Technological University, Delhi, India, and Queen's University, Kingston, Canada, and hosted by Electronics and Communication Engineering Department, NIT Silchar. I extend my warmest welcome to the first distinguished speaker of Day 2 session, Professor Ahmed A. Kishk from Concordia University, Canada. Professor Kishk received a BSc degree in Electronics and Communication Engineering from Cairo University, Cairo, Egypt in 1977, and BSc in Applied Mathematics from Ain Shams University, Cairo, Egypt in 1980s. In 1981, he joined the Department of Electrical Engineering, University of Manitoba, Canada, where he obtained his master degree in engineering and PhD degree in 1983 and 1986 respectively. From 1977 to 1981, he was a research assistant and an instructor at the Faculty of Engineering, Cairo University. From 1981 to 1985, he was a research assistant at the Department of Electrical Engineering, University of Manitoba. From December 1985 to August 1986, he was a research associate fellow in the same department. In 1986, he joined the Department of Electrical Engineering, University of Mississippi, as an assistant professor. He was on sabbatical leave at the Chalmers University of Technology, Sweden during 1994 to 1995 and 2009 to 2010 academic years. He was a professor at the University of Mississippi during 1995 to 2011. He was the director of the Center for Applied Electromagnetic Systems Research during the period 2010 to 2011. Currently, he is a professor at Concordia University, Canada since 2011 as Tier 1 Canada Research Chair in Advanced Antenna Systems. Professor Kishk was an associate editor of Antenna and Propagation Society newsletter from 1990s to 1993, and a distinguished lecturer for the Antennas and Propagation Society during 2013 to 2015. He was an editor of IEEE Antennas and Propagation magazine during 1993 to 2014, and a co-editor of the special issues Advances in the Application of the Method of Moment to Electromagnetic Scattering Problems in the ACES Journal. He was also an editor of the ACES Journal during 1997 and an editor-in-chief of the same ACES Journal from 1998 to 2001. He was the chair of the Physics and Engineering Division of the Mississippi Academy of Science during 2001 to 2002. He was a guest editor of the special issue on artificial magnetic conductors, soft and hard surfaces, and other complex surfaces in the IEEE Transactions on Antennas and Propagation in January 2005. He was a co-guest editor in IEEE Antennas and Propagation and Wireless Letter on the Spatial Cluster on 5G and 6G enabled antenna systems and associated testing technologies. He was a technical program committee member for several international conferences. Professor Kish's research interest includes the areas of millimeter wave antennas for 5G and 6G applications, analog beamforming, RFID antennas for readers and text, dielectric resonator antennas, multifunctional antennas, etc. He has published over 370 refereed journal articles and 510 conference papers. He is a co-author of 4 books and several book chapters and the editor of 4 books. He offered several short courses in international conferences. Professor Kish received the 1997 Outstanding Engineering Educator Award from the Memphis section of the IEEE. He received the Outstanding Engineering Faculty Members for the year in 1998 and 2009. Faculty Research Award for Outstanding Performance in Research in 2001 and 2005. Award of Distinguished Technical Communication for the entry of IEEE Antenna and Propagation Magazine 2011. Also, the Valued Contributor Award for Outstanding Invited Presentation from the Applied Computational Electromagnetic Societies. He received the Microwave Theory and Technique Society Microwave Prize 2004. He received the 2013 Chen Cho Tai Distinguished Educator Award of the IEEE Antennas and Propagation Society. With this, I welcome you, Professor Kisk, first for joining this session and then for starting your session, starting your first talk, because today your assigned talks are 2. First one is to be delivered on overviews of dielectric resonator antennas, followed by second talk on topic wideband dully polarized microstrip air patch antennas and dielectric resonator antennas. With this great honor, I request Professor Kish to start the session.
Thank you very much. Today, we're going to just give a very quick overview on the electric resonator antenna from the start. So the outline of this talk will be related to what is the electric resonator, and I guess all of you are familiar with all of these, so I'm going to go fast over some parts of this presentation in order to be able to cover the whole presentation because it is too long. I will present some sample results of different dielectric resonator and perforated dielectric resonator, waveguide and image guide feeding. This one, I will leave it to the end, and if there is the time, we can talk about it. And we'll talk about arrays, beamforming network, high gain DRA antennas, circularly polarized, and the reflector array. So dielectric resonators are made from material that can have a dielectric constant that could range actually as low as 4. Actually, I tried some that can go up to even 4 millimeter wave frequencies in order to increase the size. One can go up to 140 and even more if it is allowed, but we'll see what is the problem of using a very, very high dielectric constant. And these can be found as a ceramic material, as powders, and others. And actually now, there is available in the market some material that is with dielectric constant 10 that it can be used in 3D printing. And this would really open the window for many new challenges that we were facing in building these antennas before. And it can have any shape that you can imagine. As you have seen yesterday by Dr. Leong, that even some arbitrary shape like this ghost, it can resonate and it can radiate. So the problem is that, can you analyze it? Can you control it to reach to certain resonance frequencies? That is the important thing. And here we started, the first dielectric resonator was in a cylindrical shape and the hemispherical shape. And at the beginning, we were limited to the geometries that we can analyze. So some people used some approximate method to analyze the cylindrical dielectric resonator, and some people use Green's function to analyze the hemispherical dielectric resonator. And after that, with the advancement in the computational electromagnetics, we were able to actually analyze any shape. As you can see, it can take any shape. And also having dielectric resonator made not only from one dielectric constant, but we can have more than one dielectric constant, like the case of stacking two dielectric resonator, one with low dielectric constant and the one with high, that is to increase the bandwidth. Also, we found that the shape, every shape has its own characteristic and its own bandwidth. So we will talk about this later on. So the size of these to resonate at the lowest order modes, the size, of course, is inversely proportional with the dielectric constant. That means that you can control the size by choosing the proper dielectric constant. And most of the time, these dielectric resonators are mounted on a ground plane. And the advantages is that since this material that we are using, actually, it is low loss type of material, like the ceramic material, it has low dissipation loss. That means it will give us very high radiation efficiency. Unlike the concept that was related to the electric resonator in the past, that these material has very high Q, and that means has very narrow band, and it is not radiating. It's not radiating if it is shielded and use it as a resonator for filter design or oscillators and so on. But if you choose the proper modes, especially the low order modes, and it is an open structure, then it is radiating, and radiating actually very efficiently, because it will have the Q factor that will control it. It's a radiation Q factor. It is the Q factor related to the losses coming from the radiation. So that is very desirable in the antenna application. So it is expected to have wide bandwidth because it has low Q factor. And for this structure, it doesn't suffer from the problem of having the surface waves like printed circuit antennas. So here it has no surface wave, and it has also low mutual coupling than the case of microstrip antennas. And that means it will have no scan blind and wider scanning range than the microstrip antennas. And we'll give some examples about that later on. So it has more geometry parameters to achieve the design requirement. As you can see, you can take any shape, and every shape will have its own design parameters. And the more design parameters you have, the more flexibility you have. And its size is controlled with wide range of materials. Like as we can see, available in the market, very wide range of dielectric constant. Unlike in microstrip antenna and the printed circuit, it is limited from like 2 to about 10. And between these, it is like 2, about around 4, 6, and 10. So it is limited as a microstrip antennas on the availability of the material characteristics. Many possible excitation mechanisms it can fit with different scenarios, and we'll see what are the possible excitation for this. Different radiation pattern for different application. So we can have two main characteristics of the radiation. One is acting as a monopole, and one is acted as a narrow slot on the ground plane where it has broadside radiation pattern, and we can choose the mode that excites this type of radiation pattern. And the dielectric strength for the ceramic material, for example, is about 200 volt per mils. That means it has high power capabilities. And also in the temperature range, it can operate from minus 65 Celsius to 110 Celsius. And that means it can work under many different environments. And that is good for military application, where you don't know where you're going to operate your operation, in a very hot weather or in a very cold weather. So compared to the printed antennas, the advantage, it has wider bandwidth, no surface waves, more geometry parameters, size control with wide range of material, high power capabilities, better scanning at lower elevation angle. But the disadvantage, as we know, it requires more complicated analysis. And so far, there is no really an analytic solution for it that give me accurate solution for, like the microstrip antennas. People started with transmission line model, started with cavity model, and so on, where these are sort of analytic analysis for the problem. But for the dielectric resonator, the analytic analysis available is that you assume that the walls are magnetic conductor, and this is a very poor assumption that gave us really very bad prediction for the resonant frequency. And of course, the fabrication is more involved than microstrip antennas. But in terms of bandwidth, in the early 90s, when we were limited to the cylindrical shape or the hemispherical type, we had about 5 to 10% of a bandwidth. But when we use the technique used in microstrip antenna by stacking the two different dielectrics on top of each other, each is supposed to resonate at different frequency, we can have bandwidths up to 30%. And now we can reach actually a bandwidth higher than 100%. And these are the possible geometries that can achieve that. Like for this conical shape, for example, and this tetrahedron shape, we can have about 50% bandwidth. But when we have the rectangular shape, especially when it is excited from the side by a strip like this, and even when we have the dielectric over the edge of the ground plane rather than sitting on top of a flat or horizontal ground plane, we can actually have about 100% bandwidth. So wider matching bandwidths can be achieved than what we can do in printed circuits. Also, in order to understand the characteristics of the dielectric resonator, people started by analyzing the cylindrical shape and try to see what are the available modes and what are the parameters that control its resonant frequency and so on. So here at the beginning of this, we were doing this numerically, and it was a very hard search in the complex plane to find the complex resonant frequency from which we can predict the resonant frequency and the Q factor of the resonators. And here, in order to have from single calculation a wide possibility of using it in many different parameters, with different parameters, we try to normalize the radius of the cylinder to the height of the cylinder, and also the resonant frequency, it is proportional with K naught times A, and by this way, any point in any of these curves actually can represent many different dimensions for A over H constant, for example. That means you can change A and H to give you certain value. That means that you can work with any size actually with keeping this ratio. And by this, it will give you certain K naught A, and also you can control this by the dimension. And here you can see that as you increase the dielectric constant, as the resonant frequency is going down for the same size of the resonators. and also the Q factor is also can be predicted. And here you can see that the Q factor is increasing by increasing the ratio of A over H. And also the Q factor is increasing by increasing the dielectric constant. And we know that the bandwidth, usually it is inversely proportional with the Q factor. That means the higher the dielectric constant, the lower the bandwidth. And in order not to have some kind of engineering expression, we created empirical expression that can predict the resonant frequency and the Q factor. Just by using it in a calculator, you can predict what are the resonant frequency and the Q factor for certain dielectric disk. This is for the mode TM01 delta, and here we are saying 01 delta. That means has no phi variation, so it is constant in the phi direction, and it is the first mode in the radial direction. And here delta, it is given as the third index, which was supposed to be related to the height. And because the height in a cavity, it was always multiple of half wavelengths when it is binded by conductor from the top and the bottom. But here it is an open surface by dielectric, so this height never be exactly lambda over 2. That's why they use this delta, and the society never agreed on a unique definition for this. The other modes is a hybrid mode. It's combination between the TE and the TM modes, and that is always will happen if you have phi variation. And the one here means is the phi variation is like a sine phi or cosine phi variation. And once you introduce variation in the phi, TE and the TM will never satisfy the boundary conditions for this dielectric resonator, and that's why it has to be a combination of TE and the TM. For this mode, it has certain field distribution that we must be familiar with in order to know how to excite it, and as we will see. And also, we were able to get these charts for the resonant frequency and the Q factor. In fact, we have it also for HEM1-2 mode, where for single phi variation, we can have two possible modes. One with rho variation is 1, and the one with rho variation is 2. And both of them actually give us some kind of orthogonal modes that are like this one. It is mainly like the TE type of variation, while the other one is like TM type. We can say it is quasi-TE or quasi-TM type of variation. So here, in order to know where to put a conductor backing the dielectric resonator, we have to look at the field distribution. For the TE01 mode, for example, we have the electric field is in the direction of phi, while the magnetic field is a radial type. And by doing this, we know if we split this cylinder in along the z-axis, always the ground plane or the conductor will be orthogonal to the electric field. That means it's not going to disturb the field distribution of this mode. That means I can cut half of the resonator and they still operate at the same resonant frequency. For the TM01 mode, we have the radial electric field and the circumferential magnetic field, just dual to the TE. And that means if I have the conductor splitting the resonator to two half, one in the top, one in the bottom, also here I'm going to keep the field distribution and I'm not going to change the resonant frequency, although I remove the half of the dielectric resonator and replace it with this conductor plane. For HEM11 mode, these are the sketch of the field distribution for E and H, where we can see this is TE12 mode. I can split the resonator along its z-axis and still operate at the same frequency. While HEM11, which is more of us are familiar with this type because it gives us broadside radiation pattern, as we'll see, we can cut it to half, such half in the top, half in the bottom, and that means we can have half of the dielectric resonator and operate at the same frequency. So here, the radiation pattern for a single pure mode of the TE01 mode, when we split it in this form, so we have a broadside radiation pattern along the Y direction, and E and H plane are as such. And for the TM01 mode, this is, we have a null on the axis, so the radiation pattern of the TM01 mode is like a monopole type of radiation pattern, and this is one of the very critical type of modes, in a sense that you always try to excite it with a monopole along its axis, and the monopole is also have the similar radiation pattern, and you will never know what is the one is really dominating the radiation. Is the monopole or the dielectric resonator? So one has to really know in advance what is the dielectric resonator resonant frequency for the TM01 mode in order to operate at its frequency, not at the resonant frequency of the monopole loaded with dielectric material. Also, the HEM12 mode, although it has phi variation, but the phi variation is in this direction. This will give us this null on the axis, so it is acting almost like the TM01 mode radiation pattern. And the HEM11 is acting like this mode over here. It has a broadside radiation, and here is E and H plane radiation pattern. So it is very important to know the characteristic of each mode, to know what type of radiation pattern that you are looking for. Also, how to excite this mode. It is very important. Knowing the field distribution will tell us what kind of excitation can excite this mode. So we can have a simple rules on choosing the excitation, is that we can have electrical current prop normal to the ground plane along the electric field lines. If you do that, then you will couple to the mode that give you this field distribution. Or narrow slot on the ground plane along the magnetic field lines. So these simple two rules can tell you what is the proper excitation that can be used. And you have to remember that each one of these modes can be excited either by a prop or by narrow slot. And we'll see what is the effect of using a prop for some modes and the using narrow slot. For example, here, if I have an electric current prop along the z-axis located off the center by a distance rho f, and I try to find what are the mode, because once you have an excitation, although the dielectric resonator is actually resonating, or you are choosing the frequency and the size and the material that you needed to operate at for certain mode. But once you put the excitation actually it can couple to many other modes or cause perturbation that generate many other modes. And you have to choose the position that excites strongly the mode of the resonator. For example, no matter what is the resonant frequency you are operating at, if you put this monopole on the center, you always have a monopole type of radiation pattern, regardless of what is the frequency of operation. So you can see that the contribution of the HEM11 mode is really zero. I am not coupling to it at all, but I am coupling to what is possible TM0 mode. So their strength is about maybe 75% at this location. As I move further from the center by this monopole, you find that this mode is getting smaller and this mode is getting stronger, while also other possible higher order modes can be excited. But most of the time, since I am operating far from their resonance, their contribution will mainly the active type of contribution. They are not gonna contribute strongly in the radiation pattern. And here you can see the dominant or the mode that I'd like to excite is getting stronger and stronger, and the other modes are getting weaker and weaker. So the radiation pattern for the resonator, when I am my excitation at the center, is like a monopole radiation pattern. When I am halfway between the center and the edge here, you can see that the radiation pattern is in the broadside direction, but I have another type here, which is contribution to the cross polarization. So the monopole type of radiation here or contribution is acting as a cross polarization. But when I move further from the center, closer to the edge, I found that I have better performance for the radiation pattern, closer to the either radiation pattern of this mode, but still I have cross polarization contribution from due to the presence of the dipole. If I use a slot, for example, if the slot is exactly on the axis, let us say along the y-axis over here on the center, you can see it is only coupling to the HEM11 mode. So its strength is very strong, while the other modes has no contribution. But once I move off from the center, you will find that the zero order modes is getting excited, and other higher order modes is also excited. So if I look at the contribution of the radiation pattern of the total number of modes, when I am on the center, you find that the slot really giving me an ideal radiation pattern, which is a contribution of the single mode. And you can see no cross polarization exists here. But if I am a halfway, you will find, as you can see, the radiation pattern lose its symmetry because of the contribution of these other modes and the zero order mode, and you can see that the cross polarization is high. If I move further close to the edge, you can see that the zero order mode is more dominating and perturbing the radiation pattern completely. So by having this simple example, one can say, okay, if you want to excite this HE11 mode by a probe, you have to be close to the edge. If you want to excite it by a slot, you have to be at the center. And the radiation efficiency is very important to know it, and we can measure it by having two sets of measurements. You can measure the dielectric resonator or the antenna in its radiation case, like is exposed to the free space, and from the reflection coefficient that we get from this measurement, we can process the data in order to calculate its radiation Q factor. But we do another measurements where we prevent it from radiation. We shield it with a conducting cavity as such. That means it is not radiating, and the contribution, if I measure the reflection coefficient, you find that the contribution is coming due to the losses on the dielectric, from which we can calculate what we call it the non-radiating Q factor. And the radiation efficiency can be simply obtained from this expression, 1 minus the Q radiation over Q non-radiation. And in computed radiation efficiency using these two setups, it is about 99%. So the dielectric resonator has really very, very high radiation efficiency. And these are some early examples of the stacked dielectric resonator. And at that time, we have it done this experimentally. And by the way, this was just dielectric constant of 4, and this is dielectric constant of 2.2, and this is dielectric constant of 10, and they resonate nicely and they give us bandwidth about 30%. But if I change the geometry to be a triangle cross section but tetrahedron form, in a way I have the cross section on the bottom, which is sitting on the ground plane. It is smaller than the one in the top. Here we achieved about 43%. And I tell you what is the trick, why this is giving us very high bandwidth, or very good bandwidth. While if I have the cylinder in a cone shape like this, and I have it here sitting on the ground plane, I can have even further wider bandwidth. But one has to be very careful in defining the bandwidth. You don't define the bandwidth just based on the matching bandwidth. You define it based on the common bandwidth between the radiation and the reflection. Because as you can see here, we have more than one resonance. That means this structure with the excitation used can excite more than one mode, and all of them are matched. So here we can get radiation pattern completely different than this radiation pattern. So I can't, usually you have some specification for the radiation pattern, and that means you can't use this is as to define your bandwidth. So as I always say, we have to use the bandwidths that have the same radiation characteristic or same family of modes, the modes that have the same features and the characteristics. If I have the half cylinder as such, one can achieve about 35% that is coming from the mode that has a null on the axis, which is that HEM12 modes. In terms of excitation, we can use a microstrip exciting a narrow slot. And the nice thing about this excitation is that you have many parameters to control the matching bandwidth. And here, for example, this is a narrow slot excited by microstrip. It's not necessarily that you have the microstrip in the middle or in the middle of the slot. It could be off the center of the slot. And that means this is a parameters to control the bandwidth, because if this is lambda over 2, the field distribution on the slot will be almost the same regardless of where the microstrip line is. And you have the stub. So all of these are parameters that you can use to control the bandwidth. And always I say, if you know the Q factor of the resonator, that means you can have prior knowledge of what is the possible bandwidth that you can achieve from this dielectric resonator. But can you squeeze all these bandwidths? This will depend on how you excite these resonators, how you couple to these modes that give you this wide bandwidth. So as I always say, the Q factor is like a measure of the amount of juice in the orange, and you know how much juice you have in the orange, but can you get all this juice or not? It depends how perfectly you are squeezing it. So the excitation at the proper excitation is the one that can determine if you can squeeze all the possible bandwidths or not. And these are some examples for a stacked dielectric resonator. And here the dielectric constant of the bottom is 4 and the top is 12. And this is achieved 40% bandwidth with a broadside radiation pattern. And this is excited with a narrow slot and the printed microstrip line in the back of the ground plane, excited by this end connector. We can have a feeding network for 4 of them and still giving us similar bandwidths. And in terms of the 4x4 array, same way, but as you can see, as you increase the number of the element, you can increase the directivity and the gain of the system. Also here, another one dielectric resonator made in a steps like this stair type of shape. When we put the narrower base on the ground plane and the wider base on the top, you can achieve really very wide bandwidths with very good radiation pattern. So the concept here is that like you have in the core of the dielectric resonator, you have high dielectric constant and a little bit larger core, larger dimension. You have air and then dielectric. That means that the effective permittivity is decreasing as you go away from the center. And this is one trick that one can use to increase the bandwidth of dielectric resonator by having a high dielectric constant in the core and the lower dielectric constant as you go away from the core. This is like trying to have the characteristic impedance of the dielectric resonator somehow try to match it to the free space characteristic, the free space intrinsic impedance. So the core has certain dielectric mu over epsilon. That means the core has lower intrinsic impedance than the outer one, than the free space one, which is 376 ohm. Also, the stacked type, we found a problem where you can see how we can adjust this, the top and the bottom, to be exactly centered with each other. You find it difficulty if you have some kind of glue, you try to put it, and once you press it, you will find it slides a little bit, and you need to do some adjustment for that. And it sometimes is difficult to do it. So in order to avoid that, we made the lower dielectric constant as a cup as such, and then the other one is a disc that we can press it inside, and with just the friction type of contact between the two dielectric, you have it exactly on the center, and you have no problem of adjusting them on top of each other. And when we excited this by a narrow slot, excited by microstrip line, and when you put the lower dielectric constant in the bottom or above the slot, and the high dielectric constant here on the top, we can achieve really very extremely wide band in matching and a really good radiation pattern. But if you flip this in a way that the high dielectric constant sitting on this long slot, you can find it that we can lose the match. But we can gain this bandwidth if we change the dimension of the slot. So if I have the high dielectric constant on the top of the slot and the lower is above, we can reduce the length of the slot to make it resonate with this high dielectric constant, and we can achieve similar wide band with similar radiation characteristics. Also, instead of having two different dielectric material, we can have the dielectric resonator from one high dielectric constant, and we reduce the dielectric constant of the material around this by having holes. And this sort of volume type of ratio can control what is the effective dielectric constant using this expression, for example. And here we had some simulation for the exact geometry with the holes, and the one by using the effective permittivity as such as this, and we can see very good agreement between the two models. That means even with this very, very small size of dielectric resonator, proliferation of the dielectric material is possible and can be used in order to have multiple dielectric constant for the resonator based on controlling the hole size and the density of these holes, in certain region, you can control the dielectric constant, and by this way, you can increase the bandwidth, which in this case is about 50%. Also, you can have it in this form by having high dielectric constant over here, with exciting it with a probe or with a slot in the middle. Both are giving us wide bandwidth, 40 to 50% bandwidth, with very nice radiation characteristics that can have with the slot fed. This gave us the smallest possible cross polarization from this antenna. So the other type is the geometry is having the rectangular case sitting, the rectangle sitting on a horizontal ground plane with a strip excitation in the side over here that is actually connected to a coaxial probe coming with a connector from the back, and you solder it here. This can give us 50 to 60% bandwidth. But we can make the horizontal ground plane a vertical ground plane. And how we do it is just having this as a dielectric substrate. And this dielectric substrate, we can have from one side a ground plane ended at this position, and the microstrip is coming all the way here. So this is like having this excitation as printed something. This will act as a probe very close to the resonator. And by this way, we can cut the substrate to house the high dielectric constant rectangular resonator to be as such. And by this, you can find that the structure becomes more compact rather than having this horizontal area and I required all this area, I just require in a vertical form. And these are some examples for the dielectric resonator rectangular one. But when we use a solid rectangular one, we found that there are some other higher modes that are excited. And we were able to identify this mode by looking at the field distribution on the rectangular shape, and we found some very concentration of the field in this region and this region. That means that this is acting as a resonator in its own within this whole resonator. And when we removed this dielectric material, it seems like as if you have reduced the dielectric constant of this cavity. That means it will resonate to higher resonant frequencies. That means you have shifted this resonant frequency far away from your band. And by this way, you can achieve really very wide bandwidth. And here, the radiation characteristics for different at different frequencies for this antenna, where we can achieve 93% of a bandwidth with the 10 dB level of reflection coefficient, or 77% for a reflection coefficient of -15 dB. Also, another type of resonator, instead of the A shape, we make it an H shape, and at that time, we needed to be used as a sensor for breast cancer detection. That we need this, instead of having surrounding the breast with some material to reduce the reflection, the direct reflection from the breast, we attached the resonator directly to the breast. And by doing this as well, because our antenna is made from dielectric material, no conductor will be touching the tissue. And of course, the conductor could generate some heats that will make it uncomfortable for the patient. But with having dielectric, touching it, this will not cause any harm to the patient. And by doing this, we make the complete path for the A shape is just the tissue itself. That means we are assured that the signal will be strongly penetrating to the tissue. And by this, for example, we were able to predict the location of the of the tumor, which it was very, very small, and we were able to get good performance using this as a sensor for the breast cancer detection. Also, we can use the dielectric resonator as reasonably a little bit high gain by using the concept of the Yagi-UD, but we use it for dielectric resonator. We know that the Yagi-UD has three elements, like the long wire as a reflector, and the middle wire as a the driver, and another one smaller as the director. So we use this concept by having, if you look at the single dielectric resonator, as we usually have, this is the possible radiation pattern, as you can see, and this is infinite ground plane. So as you can see, the 3 dB bandwidth is almost 180 degrees, and this is the bandwidth achieved, matching bandwidth about 5%, for example. But when we have a director on top of that, that means the reflector or the ground plane act as a reflector. The dielectric resonator here is acting as a driver, and this is as a director. And you can see that the beam width becomes narrower, but surprisingly, we find is that the bandwidth is increased. We know that the Yagi-UD antenna doesn't have a wide bandwidth unless you go to the log periodic type. But here we found that we have an increase in the bandwidth. If we increase the number of the directors, we can increase the directivity, and we can even have further increase in the bandwidth. And I'd like to mention something here. This is, as you can see, although all are made from the same type, and instead of having separate dielectric resonators, we made from the same material, and we machine it, and we make the separation between them by just the same material neck over here. So we don't have to have a spacer in between. And by doing this, you can see that this resonator has a similar frequency as such, but we need another one acting or have a close resonant frequency to the resonant frequency of this. So when you have it in the top, you'll find that this also interact with the ground plane. So there are some fringing fields coming here. That means that the effective permittivity is smaller. That means the size has to be larger to operate at the same resonant frequency. And that's why, that's the reason why the upper dielectric resonator is larger than the lower one. And we built this, and here we have two excitation, one for the slot, in this case, slot fed, and here the resonator and one director, or resonator and the two directors. And you can see here the reflection coefficient have very reasonable wide bands that can reach for about between 19 and 26%. And the radiation pattern, you can see that the two directors is more directive than one director in terms of the radiation characteristics. And we did the same with probe fed as well, can give us similar characteristics. The other way to increase the bandwidth is just to reduce the effective permittivity, and to use a probe of exciting it. You will find that if we made this is like a cup flip and house the probe, and by this way we try to avoid drilling a hole in the high dielectric ceramic material to house the dielectric to house the probe. And by doing that, that means that the probe is in the free space, and it needs to be longer than when it is around the high dielectric constant. So in order to house it in here, we bend it to be like an L shape. And as you can see, we can use this cup or this shape to fit some application. Actually, for this shape, we were forced to use the shape because we need it for some application that I don't have to mention it now, but it is was one of the requirements to have this shape. And here you can see this is giving us very wide bandwidth, 32% of bandwidth. And here is one example measurement versus computed that achieve about 35% of the bandwidth with good radiation pattern. But we know that having the dipole bended as such, this will give us some contribution to the cross polarization, and that's why for this antenna the cross polarization is a little bit higher than the regular dielectric resonator. This is another way of exciting the dielectric resonator, where we can actually have it excited by a waveguide. And the waveguide is excited by a probe. There is a probe inside the waveguide that is coupled to the resonator over here. And we can have still wide bandwidth. And by this, we can have an array of this. And actually also we use the slots to do the same excitation to achieve very wide. And here, the reason of doing that we were able to make an array of these excited with the same waveguide. Also, we for arrays, mutual coupling is very critical and very important to study. So here, an example of two resonators excited by coaxial probes. And here, this is the E-plane arrangement that the polarization is along the line between the two resonators. And here, we have looked at different distance center to center between the resonators. Here, with the center frequency at 10 gigahertz, we have 10 millimeter, 15 millimeter, 20 millimeter, which are actually equivalent to 1/3 of a wavelength, half a wavelength, or 2/3 of a wavelength. The other arrangement, when we have it in the H-plane arrangement, where the polarization is orthogonal to the line between the two resonators. And here you can see that as I increase the distance between the two resonators, I decrease the mutual coupling. But you can see that the mutual coupling here is reducing slowly with distance. And here for the H-plane, that the mutual coupling is reduced very quickly with the distance between them. And the reason is the E-plane coupling is inversely proportional with 1 over the distance between the two resonators. But with this H-plane, it is inversely proportional with 1 over D squared. So if D is very small or smaller than 1, then you will find a very rapid change and in the mutual coupling, while here it is lowly. But when we started with 1/3, the E-plane is giving us lower coupling than the H-plane. And here, this is an example of measuring the mutual coupling between two resonators excited by narrow slots with a microstrip line. And as you can see, the mutual coupling is below 20 dB. This is also a linear array to show you the effect of the mutual coupling on the radiation characteristics. Here, if we have without coupling, and what we mean by without coupling, it is just if you use the array factor and you multiply it by the radiation pattern of an isolated element, you can get this type of radiation pattern if you have a broadside radiation or radiation in the scanned at 30 degree or at 60 degree. You can see here the side lobes and what is the behavior around the main beam. The main point here is that when I phase the array to give me 30 degree, I'm getting exactly 30 degrees. 60 degree, I'm getting exactly 30 degrees. But when the mutual coupling is included, and how I include the mutual coupling is just I use the full wave analysis to solve this whole array at once. And I phase the element to give me 30 degree or 60 degree. And again, with the mutual coupling, still I having the main beam directed to the same direction that I'm intended to have. But the problem here that you can see that higher side loop level close to the ground plane than the case of no mutual coupling. And that is very critical in the dielectric resonator, because the dielectric resonator is a volume type of antenna. So when you try to scan at lower elevation angle, there is some kind of shadow effect blocking the radiation pattern. You try to force it here, so this will be in the way, this will be in the way, and by this way, you can see that the effect of this on the radiation pattern coming in this form. But the important thing that there is no effect on the direction of the main beam, and that's why we say excellent prediction for the scanning direction, and it is also doesn't have the scan blind effect. If you have a microstrip array as such, and you try to scan, you will find you try to scan at 30 degree, it might come at 28 degree. You try to scan at 60 degree, it might come at 55 degree. That is because of the mutual coupling effect is strong that affect even the main beam direction. Also, you might find that in microstrip antenna, it is difficult to scan at 60 degree. You might lose the radiation pattern at this. So you can't scan at lower elevation angle with other antenna, but here we are able to do that. And this is a planar array, and the effect without mutual coupling and with mutual coupling again for the radiation along the ground plane. This is also something example to show the efficiency of the dielectric resonator. So there is a commercial radar by Ray Magin where it is made of microstrip batches, and we try to replace this array with dielectric resonator of the same size and the same arrangement and the same feeding network. And here we measure the radiation pattern in E plane and in H plane, and we compared microstrip array with dielectric resonator array, and we can see that we have almost like 2.6 or 0.2 dB higher gain than the batch antenna. This is a very huge increase in the gain. Plus, the gain in the bandwidth. The bandwidth of the microstrip antenna is about 3%, but for the array of the electric resonator antenna is actually much, much wider. For circular polarization, we can have circular polarization of a single excitation if we make the shape of the resonator in a hexagonal DRA or as an elliptic type of DRA. This is the type of impedance, real part and imaginary part, and the reflection coefficient, but the bandwidth of the circular polarization is about 3%. So if we can use this element in a subarray of 2 by 2 elements, and we phase them and arrange them in certain way, we can find that the 3 dB axial ratio bandwidth can be increased as we choose different arrangement for this. But if you have pure sequential feeding, and the sequential feeding means that if this is my starting element, if I come here and rotate it with 90 degree and phase it with 90 degree, and this is with rotating another 90 degree, that means from the reference is 180, so I phase it with 180, and this is with 270 rotation and the 270 phase. You can see that all the elements will have the same impedance, input impedance. So all have the same reflection coefficient. Not only that, but also the axial ratio is almost frequency independent. And when I say frequency independent, if you are able to maintain the magnitude and the phase at all frequencies to be the same as the center frequency, you can have the same performance, and the axial ratio is 0. what is the measure? What this mean? Why we use this kind of rotation? It's a way to cancel the cross polarization of the CB. And this is an array of 8 by 8, and you can see that the radiation pattern here is very nice. And here, the radiation pattern was based on what we call it rotating probe, like the probe is measuring linear polarization, but it's changing its direction. And that means you can see over here, this oscillation, the difference between here and here is the measure of the axial ratio in this direction. Here, you don't see any oscillation or any variation on the main beam. That means the main beam is having excellent CB, zero axial ratio. And when we made it from 4 elements, we achieved wide band and axial ratio and matching. And of course, when we use actual network, we have delay lines that has its own limited bandwidth. This is we use also in a beamforming network that is a Butler matrix for 4 elements. And here the radiation pattern, you get 4 beam by exciting each port individually, or if you feed them all simultaneously, you can get distinct 4 beam, although you are operating at the same frequency. And this is Rotman lens. Again, we can have scanning for this array. Here we have 7 inputs. That means we can have 4 different beams from 7 different beams from these 4 elements. Also, the problem of array having individual elements and you adjust each one of them individually, that is more difficult. So in order to avoid this, we made these as connected with dielectric resonator, and we put holes on them in order to reduce the dielectric constant of these, in order to have a small effect of the connection between 2 resonators. And here is the performance, no difference between this and this in terms of the performance. This is, we use the dielectric resonator also at 60 gigahertz. And here one configuration of having a dielectric resonator operating actually at high order mode and surrounded by a dielectric ring. And here, when it is built, this is the radiation characteristics of this resonator. And here, the matching bandwidth and the gain level is about 11 dB or between 10 and 11 dB directivity coming from this single element. Also in reflector array, reflector array is known that has a problem of narrow bandwidth, but if we made the elements and we adjust its phase by dielectric resonators, we can increase its bandwidth. And here is the gain versus frequency and the sample of the radiation pattern. This is for offset type, where we can have the beam off the broadside. And by this, we have presented the advantage of the dielectric resonator, wide band characteristics, high efficiency, the scanning performance, beamforming network, and the DRA reflector array. And by this, I'd like to thank all the people contributed to this presentation, my previous students, and the financial support by the funding agency. Thank you.
Thank you, Professor Kishk, for this wonderful and fundamental talk. Let me share a few queries from the participant side. The very first query is, what are the differences between TE, HE, and HEM modes in a rectangular DRA?
TE and TM?
TE, HE, and HEM mode in rectangular DRA.
TE and the TEM in the rectangular DRA? No, you see, in the rectangular DRA, the TE and the TM are equivalent to hybrid mode in the cylindrical structure. The only thing that we related to TE and the TM because when people analyze it, they are analyzing it based on surrounding side walls with magnetic conductor, and they deal with it as if it is a piece of dielectric inside a magnetic wall waveguide. And by this way, the only mode that they can see is a TE and the TM. But in fact, if you analyze it using, like if you go to CST and try to find the resonance frequencies and you look at the field distribution, you will find it is really hybrid mode. And remember, TE and the TM, it is TE and the TM to X or Y direction, not to the Z direction. The TE and the TM in the cylindrical structure, it is with respect to the Z direction.
Okay. Now, next and last query. Is there any relationship between DR shapes and possible excited mode?
You see, somehow the shape, depending on where you put the excitation, you will get the same radiation pattern regardless of the shape. The only condition is that you are exciting a mode, let us say the HEM11 mode. If the electric field is going from the ground to the ground, like a loop, half a loop, you know, regardless of the shape, you will get the same radiation pattern. So that can be controlled by the excitation, the size, and the frequency.
Okay. Okay. Now, queries from participant sides of all. Now it is up to you. If you require, you can have a break of 5 minutes, or you can carry on in lecture.
I guess I take more time here, so maybe better we go to the second presentation in order not to.
Yeah. That is up. Okay. No problem.
Are we sharing now the screen, or I have to do the same thing as before? Do you see the screen? Hello?
Yes, we are able to see the screen.
Oh, okay.
Yes,
so
yes.
I go to full.
Yeah.
Yeah.
Now we're gonna talk about like all the previous presentation. We concentrated on a single polarization, either linear single or CB single. Now here, let us look at how we can have dual polarization. And here we're gonna look at some example based on microstrip antennas and dielectric resonator antennas. But I'd like, before I start, having dual polarization is possible and easy by having the two excitation, but the bandwidth is the problem. You can achieve very good isolation in the dual polarization if you have a very narrow band. But if you have very, very wide band, in order to get this good isolation, you need to do some tricks, or you should be aware of some of the problems related to having the two polarization simultaneously. So we will see different antennas with dual polarization, and we'll see also something related to parasitic coupling, prop feeding, slot excitation, slot and the prop feeding, and also for dielectric resonator and the wide dually polarized elements. Here, it is one element, we call it magnetoelectric dipole. This was just first designed in City University by Professor Luke, and it is just a combination of electric dipole and magnetic dipole. But how we can emulate the electric and the magnetic dipole? Because it is like, you know, if you're all familiar with Huygens source, Huygens sources can give you very nice radiation characteristics. But here you can see a magnetic electric dipole made of electric dipole and magnetic dipole. Both have the same polarization. So if it is horizontal polarization, both of them are horizontally polarized, or vertically polarized, both of them are. So here how we can create it. If I have this lambda over 4 plate, lambda over 4 plate, separated with a gap, if I excite it, this is acting as a dipole, right? A dipole of 2 arms with the excitation in the middle. But the dipole can be of this width. The conductor here can be very thin, like thin wire, can achieve that. So the gap in between, its length is of the wire diameter. But if I increase the wire diameter, and here we're gonna use a conducting plate, and if I make it of lambda over 2, that means the gap that I am exciting the dipole with will have the length of lambda over 2. This have field distribution that is acting actually as a magnetic dipole. So I have electric dipole with this polarization and the narrow gap in between acting as a magnetic current, because the field distribution will be in this direction, so it has an equivalent magnetic current in this direction, but its polarization in this direction. How we excited? We excited by having a microstrip line coming from the back with this is, you know, 2 sides parallel to each other, and here the electric current or the strip is coming, and then I extend it and bend it in a form of a hawk or L shape over here. This is exciting both the dipole and the slot. By doing this, we can have really very wide band from this antenna. Here it's 53%, with very nice radiation characteristics and low cross polarization. This is a linearly polarized, not single polarization here. But how we can make it dual polarization? To do that, we come to the same dipole, and instead of exciting it with 1 probe, we excite it with 2, centered around the center. And when we do that, and this is the printed microstrip in the back of this substrate that's coming from the back, and the power divider dividing the power between the 2 arms to excite this strip and this strip. This is again giving even wider bandwidth. So when we have 2 probe excitation with the same radiation characteristics. So in order to do the dual polarization, here the single probe, dual probe, then these 2 batches we divide it to 2. So that means I have gap in this direction and the gap in this direction. So these are the original excitation here, and here I create another 2 excitation. So if you look at the sketch, it will look like this. And that means this is 1 polarization in this direction, this is another polarization in this direction. And that means I created dually polarized excitation for a wide band type of antennas. So I'd like to have good isolation between these 2 polarizations. So when we look at the structure after building it, and this was done for low frequency type of application, we can see that we have very wide band matching. And the isolation, which is coming as S21 between the 2 probes excited, the 2 ports exciting the 2 polarization, very wide band. that the isolation is better than 35 dB. This is very good isolation level required for communication and for very extremely wide band. Bandwidths better than 50%. Another, and these are sample of radiation pattern and the gain of this antenna. So here this antenna achieved about 10 dB maximum gain with this 3 dB bandwidth. Another antenna is a square batch printed on a dielectric substrate and then excited with a Hawk probe, like it is have about less than lambda over 4 from the ground, and excited with a Hawk, and another 2 Hawk from the other 2 sides. And here a ground plane backed by a substrate, dielectric substrate, where I have printed the feeding network as such. So for port 1 polarization, having the feeding network as such, power divider, and another one. But you can notice here that this is for one polarization, but this arm is longer than this arm, because what I need is 180 degree, that this is supposed to be out of phase from this. Out of phase, but I rotate the probe versus the other one by 180 degrees. This is what we call it differential feeding for this polarization. And also, in order to achieve the same thing, we have done the same thing here. This is one polarization, and this is this arm is longer than this to give us this 180 degree. So both polarization are differential feeding. The only problem with this type of monopole excitation that this horizontal vertical part and this vertical part will interact with each other, introducing stronger coupling. In order to reduce this, we put a parasitic wire here, like grounded between here and the batch, and another here. So this caused some kind of blocking of the direct interference or coupling between this probe and this probe. This could be done by creating a conducting cylinders in the middle, but conducting cylinder will be bulky. So instead, we put a two wire along between each 2 polarizations. So here is the point related wire here, wire here, wire here, wire here, while the probes are coming out from this point and this point to the outside. As you can see here, the wires are coming to the feeding network and electrically connected over here. When you look at this patch, it achieves about 37% matching bandwidth, and within the same band, we have 40 dB isolation between the 2 polarizations. So this is an excellent performance for wideband dually polarized antenna. And this is sample of its radiation pattern at different frequencies. And again, the maximum gain is about 10 dB for this antenna. When we come to the slot excitation, we can have dual polarization by having 2 slots orthogonal to each other. But there are many different configurations for that. Here, this is a microstrip batch. Underneath, this is one slot, this is another slot. This is for one polarization, this is for another polarization. But in order to provide matching, this microstrip line has to be extended beyond this point. here, exciting the two polarization, or this one versus this one. But you can see this is a dashed line. That means I have microstrip line in this side and another microstrip line in the other side. That means the two microstrip line exciting these cross slots are isolated by the ground plane between that has the slot. This is another one that have differential feeding for one polarization, because when I have these four slots and have this excitation for one polarization and the other excitation for this, by having this arm is longer than this arm by 180 degrees, actually I am trying to make this excitation differential feeding. So I'm trying to reduce its cross polarization that's supposed to have a stronger coupling with this polarization. So by this way, I can improve the isolation. So if we look at this excitation, you will find it has narrow band, 4.5%, with better than 20 dB isolation. But over here, although I am sure that the slot will have very nice radiation pattern, good isolation between the two far field radiation pattern, I have very bad isolation. And we have to know that sometimes the excitation itself could be the source of the coupling. Like this line and this line are very close, and also here are very close, causing some direct coupling from the feeding network itself. And here, same thing. So here in this one, you can see if we have physical separation between the two excitation of microstrips, we can have good isolation with wider bandwidth. But over here, as you can see, complicated circuit, and some lines are close to others. So there is possible direct coupling here, but over here we are trying to do it between two opposite currents. Like here, the power divider have one current going here, one current going here, but this one current going in one direction. So they might have lower coupling over here. But at some location, you might have a strong coupling. But the differential feeding make us able to cancel the cross polarization coming from this excitation, and by this way I can improve the isolation between the two polarization. This is an example of how to improve the isolation in a wideband antenna by trying to avoid the direct coupling through the excitation itself. So here we have two stacked batches that achieve very wide band. These batches are excited by two orthogonal slots over here, but one polarization excited by microstrip from this side, the other excitation is excited from this side. So between this microstrip line and this line, they are isolated by the ground plane between the two slots. So in order to improve the matching, we made this coupling through a fork type of microstrip line excitation, and this is also fork type of excitation. But you can see that this side is interacting with the free space, but this side is interacting with these batches and the electric material on this side. So usually, if we have a symmetry type of excitation for post polarization, we can see that the reflection coefficient for post polarization are identical. But in this case, this excitation is completely different than this excitation, so the reflection coefficient from this port will be different from this port. But what we know as well is that if I have a slot, it has high back radiation. So in order to reduce the back radiation, I need to back the back by a reflector. But if I have a reflector, conductor all the way, I create two parallel plate type of guiding structure that will excite the two parallel plate, and some power will be leaked in this direction. So in order to avoid having this two parallel plate type of structure, instead I used a crossed conductor like this, and they are acting similar to a full conducting plane. So this dipole will act as a reflector for the horizontal slot, and this dipole will act as a reflector for the vertical slot, because this slot has a polarization in this direction. So I have to reflect it by this wire. And by doing this, here you can see in this part, I have the crossed dipoles acting as a reflector over here, and the stacked and the batch on the top of this structure. If you look at the performance, you will find that you can have extremely about 40% bandwidth for matching, but port 1 and the port 2 are not identical in terms of S11 and S22. But S21, because the structure is linear, it is reciprocal. So S12 and S21 are identical, and as you can see, it is less than 32% within the whole band. Perfect isolation between the two polarization. And this is the sample of the radiation pattern without a reflector and with a reflector. With a reflector, you have less back radiation. This is another structure where I have 4 polarization. One would say, what do you mean by 4 polarization? We only have vertical and horizontal type of polarization. But if you have a monopole type of structure, so this polarization, we are not going to call it vertical and horizontal, but we can call it like theta type of polarization or phi type of polarization. While the broadside type of radiation pattern, these are the one we're going to call it horizontal and vertical polarization. So how we can create 4 polarization from a single batch? And this could be a very good element for MIMO type of antennas, for example. Here, this is our batch is circular, but we cut 4 edge slots, but we excited with in this way, like you can see a power divider 1 to 4 coming from this line, split it to 4. So this is 1 going in this direction. This is 1. So this is like, you know, E theta in this direction. All are in the same direction. And we can have also another probe coming to excite the batch from the center, from the back, like here. This is the back of the substrate where we have this feeding network for the slots. But in the middle, I can have a coaxial line going all the way and connected to the batch from the lower side. So this is to give me like the monopole type of excitation. And here, this is phi type of excitation. This will be theta type of excitation. So this is both have a monopole type of radiation pattern. While the other polarization, similar to the one that we did for the air batch, having 2 probes against each versus each other with differential feeding, and another 2 orthogonal to it. So these are the L-shaped probes. This is for this polarization, and this is for this polarization. And when you look at the feeding network that can do all of that, here it is. Like here for port 1 for the X polarization of the broadside radiation, and this is port 2 for the, and we provide the differential feeding. Here we have a hybrid coupler, and we have acting as a power divider that can give us this 90 degree plus another delay of 190 degrees. So I get the differential feeding for both of them. And here I excite the theta polarization from this by the coaxial line, as we can see. And by this, I have 4 different polarization. And this is the reflection coefficient for all of them. And we found that the phi polarization, the one that is related to these 4 slots, has the narrowest bandwidth. And here, the bandwidth for all of these simulated versus measurement, the X polarization giving us about 18% X polarization, Y polarization, while the phi polarization is close to 5%, and the theta polarization is about 10%. And when we look at the isolation between them, this is the worst is less than 20 dB isolation between all these 4 polarization, while the peak is about 10 to 11 dB for the X and Y polarization, while is about between 4 and 6 for the monopole type of radiation. So here, port 1, X polarization, port 2, Y polarization radiation pattern, broadside radiation, port 3 having the null, port 4 having a null. One is theta polarized, the other is phi polarized. So this is how you can have 4 polarization from one batch, and you can use this as a good MIMO type of an element. For dielectric resonators, you have, as we mentioned before, you have to know what is the field distribution in order to know how to couple to it. So for example, for the HE11 mode, this is the field distribution that I can excite it with a probe in this direction. But I can come with another probe over here, so it will give me another polarization in this direction. While for the TM01 mode, here is the H field, circular like this in phi, and here the E field. So you can see from knowing the field distribution, you know how to couple to these modes. For a slot excitation, it has to be in the middle, as we mentioned in the previous lecture. So if I excite the 2 polarization with 2 probes, as such, this is the reflection coefficient. So this is reflection coefficient, and this is the coupling coefficient. Is not as good as we are looking for, although we have a narrow band. So if I take this as the bandwidth at 10 dB matching, so you will find that the coupling will be between -13 and maybe -20. Why the coupling is not as good as before? Because I am using a monopole here and a monopole here. This monopole not only exciting the TE modes that the HEM1 mode that I want, but also it has the monopole mode that are parallel polarization for both of them. So both of them are directly coupled through the monopole itself. And that's why I have poor coupling between them, or poor isolation between them. So this, you can also consider it for the case of the excitation for the dielectric resonator, as we mentioned previously, that many other higher order modes are excited. So I don't have only the dominant mode or the mode that I desire, but other modes are excited. So these are the one that cause the coupling between the two ports and deteriorate the isolation between the two polarization. Okay, what about if I try to reduce this by having different shape of the dielectric resonator? So this is like a cross DRA raised from the ground by another dielectric material, or it is the same material. Then I excite this one from by a probe here, and this by a probe from over here. Again, you will see, although I can have wide matching bandwidth, but still I don't have good isolation between the two probes, because this is by itself radiating as a monopole, and this is radiating as a monopole. So that means I have also two monopole close to each other that have a strong coupling between them, and that is again deteriorate the coupling. Although it is here, it has a wider bandwidth in terms of the isolation compared to the one probes inside the cylindrical DRA. This is another one where I can have, like the microstrip, have two orthogonal slots. Each is excited by a microstrip, and I have, this is, I use the staircase dielectric resonator in order to have a wide band element. So you can see here that this, it doesn't give me good isolation over a wide band. So you can see that S21 is good only between 8 and 9, but over here it is really worse, even like reached 5 dB. So although I have two orthogonal slots, I couldn't have wide band isolation between the two excitation or the two polarization, although I have a wide band element. This is another one where I have two slots, but two slots orthogonal to each other, but exciting with two different excitation. This slot is excited by microstrip line in the back of the ground plane, but this slot is excited by a coplanar waveguide. That means the slots of the coplanar that going to the slot, this is on the ground plane itself. So you can see that almost there is a good physical isolation between the CBW and the microstrip line. And when you look, although this is a narrow band type of dielectric resonator that achieved only 5%, so you can see that the mutual coupling between them is really not bad in a wide frequency range below 22 dB, much better than before, by having two different types of excitation. Or one can have a circular slot excited orthogonally by two microstrip line, but the problem that I don't have enough to improve the matching of the dielectric resonator, because if I extend this and this, they will meet with each other because they are both are printed on the same substrate. So you can see for this, I have good isolation, but in a very narrow band, because also the element is narrow band. Another one, the coplanar, instead of exciting a slot, I can make it to excite a monopole inside the resonator, and another narrow slot over here excited by microstrip line from the back, and this one will give me a very good isolation, better than 33 dB over very wide band, but the dielectric resonator itself is not wideband, so the matching bandwidth is not that wide. So having two excitation as such can also improve the isolation between the two polarization. So we used this in a wideband element, one probe coming from the CBW, and the narrow slot is excited by microstrip line, and you can see we have wider matching bandwidth and good isolation, even better than 42 dB. You can also have microstrip line instead of CBW exciting a probe. Microstrip line connected to a probe and the slot or signal to it. But I have to mention something, that here, in order to connect the probe to this microstrip, which is in the back of the ground plane, you have to make a circular hole and pass the probe through it to connect it to the microstrip line. So this is like a circular slot that you have to do in order to pass the coaxial probe to be connected to the line. And this also gave us good isolation between the two polarization and in a very wide band, although the dielectric resonator itself doesn't have this wide band. This is another type of excitation where I can have a vertical substrate where I put my excitation printed on it like microstrip lines. But here I have the end of the substrate. I put a horizontal ground plane and I open a slot. You see here, this is the edge of the ground plane that has a substrate, and I have a slot and the slot of the width of the dielectric substrate, and here the other line coming from either microstrip line that can go inside the dielectric resonator, or even I can make it CBW going all the way to the dielectric resonator. So this is also, it is similar to having, the slot and the probe type of excitation. This is supposedly will give us good isolation. But why one can come to this configuration? Because could be in array, you need, like, suppose you will have your network, not only the parasitic exciting network, you can have all transmitter printed on one side over here. So you need large area that is larger than whatever between the element in an array environment. But here it will provide you wider area to put your devices on the same board. So this gave us very good isolation between the two polarization, better than this 24 dB, and good radiation characteristics. And this is the other wideband element that we talked about it before, but instead of L shape, we make it Hawk shape in order to, because we need a lens that can pass the middle of the resonator. It will couple to another one in a differential feeding, so we bend it here to avoid that. And by this way, I can have differential feeding for each polarization. And in this way, I can have good isolation between the two polarization, although I have probe excitation. So for probe excitation, to cancel the monopole type of interaction or coupling, you use differential feeding for each polarization. By using the differential feeding, you can sort of, is like you are exciting the TM0 mode twice opposite to each other, out of phase, so they cancel each other. And by this way, you can have very good isolation between the two polarization with very nice radiation pattern. For the dielectric resonator, we have done the same as we did for the stacked batches. We have wideband resonator, the staircase, and we have the ground plane with the slot, cross the slot. Each are excited from one side of the resonator by the fork microstrip lines. And again, by doing that, we can achieve wide bandwidth matching and good isolation. So the isolation is much better than 30 dB in a very wide band, in about 40% bandwidth. And this is the kind of radiation pattern that you can see for both polarization, for vertical polarization and for horizontal polarization. And the main thing you observed here is that the cross polarization level is really very low. Another way to have dual polarization, instead of having a single element excited by two excitation, you can have two elements orthogonal to each other. So this is one polarization, dielectric resonator, excited alone for one polarization, another one excited by the other polarization. And by doing this, you can have a reasonable, in a wide band, reasonable type of isolation between them, although you have a monopole type. But if you want to improve it further, you can have this differential FET and this differential FET. So each, like if in an array environment, for example, you will have an array of horizontal polarized element, an array of vertical polarized element interdigitized with each other, and can give you a wide band matching and can give you good isolation between the two polarizations. So here, for example, a case where we have, instead of using the prop, we have used symmetry to avoid differential feeding. We have used printed on the back of this side a Bois-Tie antenna that is excited by a microstrip line on a vertical substrate, where one side is ground plane, the other side has a microstrip line connected as such. And by this, you can see that I have very, very good isolation between the two polarization, because no contribution is coming from this vertical portion of the excitation, because this is a non-radiating microstrip line printed here. So this vertical part is not contributing, and the contribution are coming from perfectly orthogonal bow-tie that excited this dielectric resonator. So we can conclude that we have several techniques that can really excite a dual polarization for wide band with good isolation. So the important thing in order to have good isolation is to could have physical isolation between the feeding network, like the case when we put the ground plane between the two excitation, or you should have differential feeding for each polarization, or at least for one polarization to cancel the cross polarization produced from this polarization that's actually causing the interaction with the other excitation. And use combination of different excitation, like when we use for one polarization a slot, the other polarization a probe. This is also can improve the isolation, or one can use two elements orthogonal to each other, like two antennas, one for each polarization, arrange it orthogonal to each other to have small mutual coupling between them. And I thank you. And if you have a question, we're waiting for your question.
Thank you, sir. Thank you very much. But I apologize to the participant for not sharing the query, because it is like 2 hours continuous talk from expert side. I will take the queries from the participant. If possible, then I will mail it to you, or directly they may contact you later on. It will be good for you. Okay. With this, thank you, Professor Kish, for accepting our invitation, for agreeing to deliver the talks in spite of your busy and hectic schedule that you shared somewhere in your mail conversation. And then special thanks for a very informative delivery in these 2 consecutive lectures. With this, I must say thank you and good morning again, and have a nice day.
Thank you. Same to you.
Thank you. Thank you, Professor. Thank you. Now, you please stop the presentation. Stop that presentation so that other speaker will come in the queue.
Okay.
You just click on that same icon.
Turn off.
You just click on same icon from where you start the presentation. Yes. Yeah. Yes.
Okay.
Okay.
Thank you.
Thank you very much. Now, before going into the third session of the day, I would request to Professor R.K. Gangwar to share his screen first, and after that I'll be going to introduce Professor R.K. Gangwar to the audience. Yeah. Okay. Thank you, Professor Gangwar, for joining us in too late from India time zone, because several observations were there on this last lecture of the second day. But anyway, we are happy to see you in this third session. And like before, for introducing Dr. Gangwar for the participants, Dr. Gangwar received the BTech degree in Electronics and Communication Engineering from Uttar Pradesh Technical University, Lucknow, and PhD degree in Electronics Engineering from the Indian Institute of Technology, Banaras Hindu University, Varanasi, India in 2006 and 2011 respectively. He is currently Associate Professor in the Department of Electronics Engineering and Associate Dean, Sponsored Research and Industrial Consultancy at IIT ISM Dhanbad, India. He has authored or co-authored over 100 research papers in reputed international journal and 80 research papers in conference proceedings. His research interest includes dielectric resonator antenna, microstrip antenna, and bioelectromagnetics. He is guided and guiding 15 PhD and 19 MTech students. He has completed an ongoing 8 R&D projects of sanctioned amount of around 2 crore Indian rupees related to dielectric resonator antenna and their application from various funding agencies like DRDO, SERB, DST, ISRO, etc. He is the recipient of INSA Visiting Scientist Fellowship and IET Srimati Ranjana Paul Memorial Award for the year 2020. He is a senior member of IEEE and IEEE APS Society, member of IET UK, life member of Institution of Engineers India, and fellow of IET India. He is also member of IET Executive Council and Joint Regional Secretary at IEEE Ranchi Center. He is also an external expert in peer review committee of project related to chaff application of defense laboratory Jodhpur DRDO. He is a reviewer of IEEE Antenna and Propagation Letter, IEEE Antenna and Propagation Magazine, IET Microwave Antenna Propagation, IET Electronic Letter, MOTL, etc. With this, it's my utmost privilege to invite Professor Gangwar for starting the session.
Okay. Thank you very much, Professor Khan, for such nice introduction. And again, thank you to give me the opportunity to share my thoughts with this prestigious Indo-Canadian Spark course. Thank you very much once again. So that is basically my outlines for the today's presentation. Here we are basically here, I think. Yeah. So here I'm going to discuss about some fundamental about your MIMO DRAs, especially what is the MIMO technology and what are their challenges and how we are able to deal with these challenges, along with some of your work which I have conducted during the last 5 years based on these MIMO DRAs. So the first is basically I consider what is the current requirement of your modern wireless communication system. So as we know that in the modern wireless communication, our first task is that we have to provide the communication for each and every user. And if we are basically going to go for our current situation in our country where the number of population is very, very high, and the demand of each and everyone is going to be high. So that means in the current situation, we require the communication system that going to be support the high data rates, improved reliability, and the high channel capacity. So the high data rate is basically going to be useful when we are basically going to go for their online streaming, or we are going to go for their video transmission or high data rate transmission. So in that condition, we require very high data rates. And then the improved reliability. It means here we require such kind of their system where we are basically going to be have the reliable, so that our information is going to be safe and it is going to be delivered proper to your receiver side. Then third one is that basically high channel capacity, which is basically going to be have the important scenario in the current situation where our task is that we are able to provide the services to each and everyone. So that means whatever the communication system we are going to be developed, that should be able to accommodate all the users which are currently available. So how we are basically going to be get all these requirement into your modern communication system. So here the possible solution to get all these things in a one system with the help of your multi-input, multi-output antenna systems. So here by using this multi-input, multi-output technology, we are able to incorporate the high data rates, improved reliability, and high channel capacities. But when we are basically going to be go for all these kind of your good things, then the system is basically going to be go for some complications. And due to that complications, we are going to be get some problems or disadvantages with this uniquely defined system, that is your MIMO antenna system. And what is the major problem which we are facing when we are going to be design any MIMO antenna system? The problem is that basically high mutual coupling or low isolation between the antenna elements which are present in the MIMO system. So as you know that the multi-input, multi-output, that means we can say that we are going to be have more than one antennas at their receiver side and more than one antennas at their transmitter side. So at the receiver side, we are going to have more than one antenna. Similarly, at the transmitter side, we are going to have more than antenna. So the mutual coupling between the antenna elements, whether at the receiver side or the transmitter side, is the major problem in your MIMO antenna system, because due to that mutual coupling, the performance of your MIMO antenna system is drastically degraded. So here our task is that we are basically going to be focused how we are basically going to reduce this mutual coupling so that we can improve our MIMO performance. So second thing is that how we are going to be increase the number of ports. That means indirectly we can say that how we are going to be increase the number of antenna elements so that we can improve the system capacity, which is basically our requirement here, system capacity. And third one is that basically you minimize the correlation between the antenna elements within the MIMO system. So here if we are basically going to be discuss the mutual coupling, then here we are going to be define this mutual coupling in two different ways. The first one is the basically your port-to-port coupling, where we are going to be we are going to be define this coupling with respect to your S parameters or reflection coefficient. And second is the basically your correlation or field coupling. That is basically going to be defined with respect to your far field distribution of your individual antenna elements. So if we are basically going to be focused on their MIMO antenna systems, especially for their dielectric resonator antenna case, then the field-to-field correlation is going to be there much more important, because that is basically going to be put maximum effort to degrade the MIMO antenna performance. So here we are basically going to be focused on their both kind of their things. That means how we are going to reduce the port-to-port coupling or the correlation between their field couplings. So both points we are basically going to be discussed here to get your better performance of your MIMO antenna system. So now, before we are going to go further MIMO antenna system, first I am going to see what are the problem which we are facing into your earlier established communication system. The initial system, that is the most fundamental system, is the basically single input, single output system. So in the single input, single output system, we are going to have one antenna at your transmitter side and one antenna at your receiver side. That is the meaning of their single input and single output here. That means we are going to use one antenna at the transmitter side and one antenna at your receiver side. So that is the basically your most simplest form of their communication system, which in general, if you see that you are going to be studying into their analog communication subject during your undergraduate classes. So that is the major or best communication signal or best communication system in terms of their simplicity and cost and the performance also. But when we are going to be go for the analyze the system for the current situation, then we are going to be have some problems in the system. What are the problem here? If you see, we are going to be have your medium between your transmitter and receiver, and within this medium we are going to be have there some kind of the problem. The first is the basically noise, and second one is your fading. And due to these two things, our signal strength is basically going to be degraded, and that is a basically major problem into your single input, single output system. Second thing is that if you see for that particular example, we are going to be have your transmitter, and here we are going to be have this one signal. So when we are going to be transmit the signal from the transmitter side, then in between the transmitter and receiver, we are basically going to be have their medium, and this medium can be anything. If we are going to be talking in terms of their city region, then we can say that we are going to be have their high buildings, high altitude buildings, or we are going to be say that we are going to be get their different kind of your trees. And if you are going to be see that if you are going to be near to their sea region, then you are going to be have their sea surfaces. And if you are going to be have into your hilly region, then we are going to be have the hill or terrain type of their things. So here in during the in this medium, we are going to be have the different kind of their environmental things. So here, if we are going to be consider that situation, then that signal which are going to be transmitted from the transmitter side, that is going to be take any path, whether it is going to be from this path or it can take this path. In both conditions, we can say that your signal is going to be traveling through your different distance with different time domain. So when we are going to be analyze this signal at your receiver side, then due to the signal which is going to be follow their different path, they are going to be reach at their different time slots at their receiver side, and also they are going to be go through their different environmental conditions. Due to that, the signal is basically going to be go through their different kind of their problems here. So here what will happen if we are going to be go into the receiver side, then the signal is going to be traveling from their more than one different paths. So at the receiver side, they are going to be get at their different time schedules and different time slots with their different characteristics because of their noise and fading which is available into their medium. So due to that, what will happen at the receiver side, we are going to be have their problem of their interference that is basically going to be get due to their multipath propagation. And due to this multipath propagation, the signal is basically going to be drastically degraded. And when the signal is basically going to be degraded due to this multipath propagation, your link capacity and ring reliability both are basically going to be degraded here. So this is the basically your major problem that we are faced due to this particular established communication system. So what are the technology, what are the concept by using that we are able to solve such kind of their problems? So here the major problem into this single input single output system is the basically your multipath propagation. So here in the recent times, if we are basically going to be see the literature, then this multipath propagation, which is the basically your major drawback into your SISO system, the same concept is basically going to be explained or basically going to be used in different manner, so that the multipath propagation, which is the problem into your original, that is your old system, there that multipath propagation is going to be get some advantage into your new system, and that advantage we are basically going to be explained with the help of your concept of diversity. If we are going to be see the diversity, then we can say that combining of independently fading signal path, that means that is basically going to be support the multipath propagation. So here we can say that the multipath propagation, which is a major drawback into the SISO system, the same concept is basically going to be give the another new dimensions of your modern communication system, where we are going to be use this concept to achieve all the requirements which is going to be required into your current communication system. So here we can say that we can achieve this diversity by creating several independent paths between the transmitter and receiver. That means multipath propagation. So here we are going to be create the multipath propagation to get your all these advantages into your current communication system. Similarly, if you see into your single input, single output system, that is the basically major problem. But here, now in the current or modern communication system, we are going to be create such environment so that we are going to be get your following advantages. What the advantages? That means that each path fades independently. What does it mean? That means the signal is going to be go for your different kind of your paths. For example, we are going to be have this transmitter side, and that is a receiver side. The signal is going to be transmitted from the transmitter side. That is going to be have these three different paths, 1, 2, and 3, and each path is going to be traveling from their different. The signal is going to be traveling from their different path. So here the each path is going to be go for their different environmental condition. So we can say that we are able to get these signal is going to be get their different kind of their environmental condition, and due to that they are going to be exposure of their different kind of their fade or different amount of their fading and the noise. So here, due to that condition, there is a less chances or very less chances that they all will fade together. So here, if you see in terms of the probability, if we are able to create more than one path into your communication system, then we can say that there is a chances, there is a maximum probability, so that we are able to get at least one signal that is going to be have your greater signal conditioning or greater signal power, so that we are able to receive that signal much effectively, and we are able to get your information in reliable manner. So here you can see that with the help of your diversity concept, we are going to be use this multipath propagation as a new era for your modern communication system. So when we are going to be apply this concept of the diversity, then we can say that the signal degradation is going to be decreased, and due to that our link performance is basically going to be increased. So here we can say that we are able to enhance our system performance by applying the concept of diversity, and this concept of diversity is totally based on the multipath propagation. So here, if you see, we are going to be categorize this diversity into the three different parts. The first is the basically your time diversity. So if we are going to be explain this time diversity, it is nothing. It is a, you can say that this is simply based on your similar concept that you have already stated. If I'm going to be explain this time diversity, then I can say that the transmission in which signal representing the same information are sent over the same channel at different time. That means we are going to be use your TDMA concept, TDMA type of those things. That means we are going to be use your different time slots to send the same information. Similarly, if you go for your frequency diversity, it means by using two or more widely spaced frequency channels to send the same message, usually at the same time, just like your FDMA kind of your things. But we are going to be use here frequency diversity. That means we are going to be control the frequencies. So we are going to use more than one frequency signals to separate your channels, so that we are able to transmit the same signal in the same slot simultaneously, so that we are able to get at least one signal at the receiver side. Third one is the basically your space diversity, and here that is the basically our area of interest here. So if we are going to be define the space diversity, then I can say that it is a method of transmission or reception or both, in which the effect of fading can be minimized by the simultaneous use of two or more physically separated antennas. It means if we are going to be apply the space diversity, then we require more than one antenna at your transmitter side and more than one antenna at your receiver side, so that we can say the space diversity is the backbone of your MIMO antenna systems. So we are basically going to be go for your space diversity in your MIMO antenna system. Now we are going to be go for your MIMO configuration. So if we are basically going to be define the MIMO, it means multi-input, multi-output. So we can say that it is the antenna technology for wireless communication in which multiple antennas are used at both the source and destination. That means we can say that we are going to be use more than one antenna at your transmitter side and more than one antenna at your receiver side. And in between we are going to be have your medium, and this medium is going to be play a lot of role for giving your noise and feeding into your communication system. So when we are going to be go for this MIMO configuration or MIMO antenna system, we are going to be have following advantages: the higher capacity, increased data rates, increased coverage, lower bit error, and improved position estimation. So if we are going to be see here, we are going to be use more than one antenna system. That means we are able to support more than one signal. That means if we are going to be talking in terms of their system capacities, so that is basically going to be directly related to their number of antennas. If we are going to be increase the number of antennas, you are able to increase the capacity. Similarly, you increase the data rates, because here you can see that we are able to transmit simultaneously one signal at the same time. In such manner, we are able to get these following advantages. But when we are going to be have some advantages, then the system is going to be have some disadvantages also. The major disadvantage is the basically your computational complexity. So here, if you see that in case of your single input, single output, we are going to be have one antenna at your transmitter side and one antenna at your receiver side. So in that condition, we are able to receive the signal, and that signal is basically going to be processed here. But now if you are going to be seen this particular condition, for example, this is your 1, 2, and 3. We can say that we are going to be have your 3x3 system. So at the receiver side, you can see that antenna 1 is going to be receive 3 signals, one from your antenna 1, antenna 2, and antenna 3. Similarly, your antenna 2, similarly antenna 3. So we can say that this receiver needs to the capacity or capability so that it can process 9 signals at the same time. That means the complexity of the receiver is going to be increased. And when the complexity is going to be increased, that means the processing cost is going to be increased. So that's why there is a major disadvantages with respect to this particular kind of their system here. Now, if we are going to be go for their MIMO techniques, then we are going to be have 2 different methodology. By using, we can improve the communication links. The first one is the basically spatial diversity. Second one is the basically spatial multiplexing. So in the spatial diversity, we can say that the same information is sent across independent feeding channel to combat the feeding. So what does it mean? That means here we are going to be have their one information signal 101. So we are basically going to be transmit the same information from all the transmitting antennas. So here, if we are going to be transmit the same signal through your each and every antenna, so at the receiver side, it is the maximum probability we are able to receive at least one signal. So that's why we are going to be say that this concept is basically going to be give the major reliability of your system. Now, second one is the basically spatial multiplexing. So in the spatial multiplexing, each bit of data stream is multiplexed on different spatial channel. So here what we are going to be do, we are going to be have the one signal is 101, and we are transmitting the signal by bifurcating 101 with your different transmitting antennas. That means each antenna is going to be transmit different signal. So what happened? Due to that, we are able to transmit more number of your data with respect to your time. So here we can say that we are able to improve the data rate and link capacity by using your spatial multiplexing concept. So that is basically totally depending upon to your application, whether you will go for your spatial diversity or spatial multiplexing. For example, if we are basically going to be design the system for your defense application, where the reliability is the utmost importance, where the information is going to be reached safely at the receiver side, that is a major important. We will go for their spatial diversity. Now, when we are going to be go for your high data rate, like we are basically going to be go for your video transmission or the online video transfer or online chatting, all these things, in that condition, we require high data rates. Then we are going to be refer your spatial multiplexing. So which techniques you are going to be used, that is totally depending upon to your what kind of your application you are targeting. Now, the performance matrices of your MIMO antennas. So here the performance matrices means what are the parameters on the basis you are able to compare the performance of your MIMO antennas, or what parameters on the basis of that you can see whether that antenna can be useful for your practical applications or not. So here we are going to have some important parameters which are going to be useful to define the performance of your MIMO antenna systems. The first and most important parameter is basically your envelope correlation coefficient. So if we are basically going to define this envelope correlation coefficient, then we can say that it basically tells us how independent two antennas radiation patterns are. That means we are basically going to say that the envelope correlation coefficient is basically going to give the idea about the correlation between your fields, or we are basically going to define this parameter how much the communication channel are isolated or correlated with each other when using simultaneously. So that means this ECC is going to give your complete information about your correlation or your isolation here. So that's why we are basically going to calculate this value by using your two different parameters. The first calculation based on your S parameter, and second calculation is based on your 3D far field pattern. So when we are going to use your S parameters, that means we are talking in terms of your port-to-port isolation. Clear? So from that port-to-port isolation, we are able to calculate your ECC. And when we are going to use this 3D radiation pattern formula for calculation of the ECC, that means we are targeting your field correlation, that is your far field pattern. So both the formulas is basically going to be shown here. The first is basically based on the S parameter, and second one is basically based on your radiation pattern. So both formulas is basically going to be utilized to define your correlation coefficient or envelope correlation coefficient. But in general, for their MIMO antenna elements, this correlation is going to be much more important, because that is basically going to give the actual value of your ECC. Now, the second parameter is basically your diversity gain. So if we are basically going to define the diversity gain, we can say that it is the increasing signal to interference ratio due to some diversity in techniques, or we can say that how much the transmission power can be reduced when a diversity scheme is going to be introduced. So here we can say that this diversity gain provides the improvement into their multi-antenna system with respect to their single antenna system. So we can calculate this diversity gain with the values from their envelope correlation coefficient, and for the practical, the value close to 10 is basically going to be considered for your best optimization or for best performance. Now we are going to have your mean effective gain. So in the mean effective gain, we can say that it measures the antenna performance where the effect of environment is taken into the account. So effect of environments means, that means what kind of your system we are basically going to be consider. Like when we are going to be go to your line of sight communication or non-line of sight of communications. In both conditions, we are basically going to go for your mean effective gain, or when we are going to consider your different kind of your environments. In both conditions, we are basically going to see what the effect onto your mean effective gain. In general, the difference between your mean effective gain should be less than 3 dB, which is basically your practical value for getting your best optimization performance. After that, we are going to have another parameter which is known as your channel capacity loss. So this channel capacity loss is basically going to give the information about your maximum data rate up to which message can be constantly transmitted over the communication channel. And the value is basically going to be required 0.5 bits per second per hertz. And we can calculate this channel capacity loss by using the following formulas. In some books, we are going to have some more parameters which are basically going to define your MIMOs, like your TAR, total power. So that is basically also going to be defined here, but I'm not going to be considered here for that particular topic. Now, what are the minimum requirement of your MIMO antenna system. So here, when we are going to design any MIMO antenna system, what are the minimum requirement? So how we are going to be, if you are going to design your any antenna system, then you have to set something on the basis of that. You can see, yeah, I am able to do it. So here I have designed these 5 different steps. Based on that, I can say that is basically going to be have your good MIMO antenna system. So the first requirement is that basically your MIMO antenna system consists more than one port. That means it is a primary requirement of your MIMO antenna system. Here we required more than one antenna elements at the transmitter side and at your receiver side. So whenever you are going to design any MIMO antenna system, first you have to see how many ports are there and how many antenna elements are there. Second thing is that all the ports associated with the MIMO antenna should share the same impedance bandwidth. And that is basically your second prime condition. So if we are going to design MIMO antenna system for example, for sub 6 gigahertz, then that is a prime condition is that all the MIMO antenna elements must cover up your sub 6 gigahertz bandwidth. Only then we are able to use that designed MIMO antenna system for that particular application. So here I have considered one example where I have used your two antenna element system for your MIMO applications. So here we can say that we are going to have your DR1 and DR2. Both are going to be fed by your port 1 and port 1 and port 2. And if you analyze this port 1 and port 2, both are basically your orthogonal to each other. So here we can say that our first condition is going to be fulfilled. That means we are going to have your more than one antenna elements. We can say that now this is a MIMO antenna system. The second thing that we have to check whether they are going to be share your same impedance bandwidth or not. So here I have plotted your S parameters. So by checking your S parameters, I can say that both the antenna elements is basically going to be share your same impedance bandwidth. That means our second part is basically going to be correct here. Now we are going to see the isolation values between your ports should be more than 12 dB. That means the minimum requirement for your port-to-port isolation is 12 dB. So here you can see that the S12 is basically going to be defined your port-to-port isolation, and that is basically less than your minus 20 dB. So we can say that our third point is basically going to be fulfilled here. Now the fourth point is that the envelope correlation coefficient values must be less than 0.5. So here, based on to your S parameter theory, I have calculated your ECC. So you can see that within the required range, your ECC value is very smaller than the 0.5. So we can say that our system is basically going to be give your good ECC value, but this value is going to be based on to your S parameters. That is not basically based on to your field correlation parameters. And the last point is the basic MIMO antennas with spatially separated radiation pattern is most preferred. Because spatially separated means your correlation is basically going to be very small. So here you can see that we are going to have your orthogonal excitation. So that means if we are going to see your field distribution, we are going to get your HM11 delta mode in both the DRAs, and both the field is basically going to be orthogonal to each other. So in that condition, we are going to say that is the basically going to give your minimum correlation between each other. So that means if we are going to calculate the ECC value with the help of your far field parameters, we are able to achieve your ECC less than 0.5. But that ECC value is going to be greater than your ECC value with respect to your S parameters. That is a general observation in case of your MIMO antenna system here. Now the MIMO antenna elements, if you are going to see your literature, we are basically going to get your 3 major important antenna elements for your MIMO applications. The first one is the basically your MIMO antennas based on to your microstrip patch technology, then slot technology and PFA technology. And all these antenna elements you can change with respect to your particular requirement of your application. Now why we are going to go for the dielectric resonators? So I'm not going to go in detail for the dielectric resonator antennas because from the last 2 days each and everybody is basically going to go for the fundamentals of your DRA. So I'm skipping this part. Now the isolation improvement techniques. So here our task is that we have to design our MIMO antenna system in such a manner so that our isolation values we are able to improve, so that we are able to get your better MIMO performance. So if we are basically going to be going to the literature, then we are basically going to be have 5 most important techniques. With the help of that, we are able to improve the MIMO performance or diversity performance of their MIMO antenna systems. So the first and most important is the basic generation of their orthogonal modes, then excitation of their degenerates modes, then introduction of their DGS, use of decoupling structures, and introduction of metasurfaces or FSS or EBG structures between their two DRAs. So here I am going to discuss your one by one. So the first one is the basic generation of their orthogonal modes. So here, this is the basically one of their most easy techniques to get into your system. So it is easy to generate and does not affect the radiation characteristic, since this method does not require any extra structure. So here you can see that in the orthogonal mode, we are basically going to have this port 1 and that is the port 2. And both are basically orthogonal to each other. In that condition, if we are basically going to be see your port-to-port correlation and field-to-field correlation, both are basically going to be your minimum values. So that kind of your system is basically one of your most important techniques and most useful techniques for your isolation improvement. But we cannot basically going to be go some beyond values by using these orthogonal modes. Now, second one is the basically your excitation of the degenerated mode. So degenerated modes means 2 different modes which are going to be have the same resonant frequencies. So here this concept is also very, very important and very useful, but it is suffering from the problem that means the difficulty to excite 2 different modes at the same frequencies. As we know that in the DRA, each and everything is going to be focused with respect to your mode of excitation. So here to excited your degenerated mode inside your MIMO is the one of your biggest challenge. If you are able to do it, in that condition, we are able to get your better MIMO performance. And third one is the basically your defected ground structure. And the defected ground structure means we are basically going to remove some portion of the ground plane in between your antenna element to reduce the port coupling. So here the technique is very, very innovative, or we can say that is going to give their very, very good results in terms of their isolation. But another side that is basically going to be affect the radiation characteristics of your antenna in terms of their gain and radiation efficiency. So whenever you are going to be using your DGS concept, you have to see what kind of your radiation performance is going to be degraded, whether it is going to be useful for you or not. Then use of decoupling structure. These are the basically your extra matching circuits in between their antenna elements to get your isolations. So here we can say that when we are going to be put your extra decoupling structures into their antenna elements, in that condition, your antenna radiation characteristics is basically going to be affected. And the last one is the basically your introduction of your metasurfaces or frequency selective surfaces or EBG to improve the isolation. So here we are basically going to be put these especially designed your structures in between your antenna elements so that we are able to get your better isolations. But here the major problem is that we require the very good precision to place these structures in between their antenna elements or top of their antenna elements. Second thing is that these structures is going to make your antenna system bulky. But the performance is basically going to be very, very good in case of your FSSs or EBG or PRS or any kind of your metasurface or metamaterial structures. So that is totally depending upon to your application, which kind of your techniques you are going to be used to get your better understanding or better MIMO performance. So here I will discuss about these 2 major antennas. The first is the basic your back-to-back geometry. So here what I have used your 2 antenna elements, DR1 and DR2. Both are basically going to be placed in back-to-back manner. That means that is the basically our substrate, and one DR I have placed onto your top side, another one I have placed onto your bottom side, and each DR is basically going to be excited by your 2 different ports. So if we are going to be see your top one, then we are using your CPW conformal strips to get to energize your DR. And if you see the port 1 and port 2, both are the basically your orthogonal to each other. And similarly, if you are going to be see your bottom one, then we are going to be have your that is also going to be excited by your 2 ports, and both ports is basically going to be have your conformal strips to get the excitation here. So here, if you see or analyze it, we are basically going to be have there 2 important concepts. The first one is the basically your orthogonal mode generation. Second one is the basically your DR orientation. And by using these 2 important concepts, we are able to improve the isolation of your antenna system. So here, first thing is that we are basically going to be analyze what are the requirements. The requirement is that first we are going to be have more than 1 antennas. So here we are using their 4 ports and 2 elements. That means our number of ports is more than 1. So that means this is definitely our MIMO antenna. Second thing is that whether all the elements are sharing their same impedance bandwidth. So from their S parameters we can check it. All the element is going to be share their same impedance bandwidth. And third, we are going to be see that the isolation, that port to port isolation is better than 12 dB. So you can see that here in both conditions we are going to be get their better than 12 dB. So that means our third concept is also basically going to be fulfilled here. And if the port to port isolation is good, that means we are going to get their good ECC, and then we have to check their last one, that is your field correlation. So here when we are going to be see about your field correlation, so here if you analyze your structure, we are going to be use your orthogonal feeding mechanism. That means we are going to be generate your orthogonal modes. So here you can see that for the port 1 and port 2, we are basically able to generate your HM11 delta mode, and that is the basically your orthogonal to each other. Similarly for your DR2, you can check it here. So here we can see that we are able to generate the orthogonal modes inside the DRAs by using this orthogonal mode excitation mechanism. So that's why we are going to be say that we are able to get your better isolation, that is your better field to field correlation. Second thing is that we have placed your antenna in back-to-back manner. That means one antenna is going to be radiated to your broadside direction, that is your positive Z direction, another one into your minus Z direction. So if you see the port 1 for your top antenna, that is your DR1, which is placed on your top side, it is going to be radiated into your plus Z direction. But port 4 is going to be excited your bottom DRA, that is going to be excited into your negative Z direction. So here the field correlation between your DR1 and DR2 is very, very low, because both are going to be 180 degree to each other. In that condition, our field correlation is going to be improved here. So if you can check for all the ports. But when we are going to be see the port 1 and 2 here, or 3 and 4 here, you check it here. So that means if we are going to be consider the top DRA, that means port 1 and port 2, in that condition, both port is going to be radiated into their same direction. So for that field correlation, we are going to be improved with the help of their orthogonal mode generation. But if you are going to be go for your top to bottom, port 1 to port 4 and port 1 to port 3, similarly port 2 to port 4 and port 3 to port 1, they are going to be radiated into their 2 different directions. So that means by using these 2 techniques, by generating the orthogonal modes and with the 2 DR different orientation of your DR, we are able to get your better field correlation here. That means we are able to improve our isolation by using these 2 technologies, or by using these 2 techniques. So here I have used your another techniques, which is basically known as your orientation or placement of your DRAs along with your orthogonal mode generation. So I have combined these 2 techniques, and based on these 2 techniques, we are able to get your better isolation in the design antennas. So here you can see that we are able to get your better values of your isolation, better than 15 dB. So that is a basically fabricated structure. So you can see that it is a very, very compact structure, and that is going to be support your 4 ports and 2 antenna elements. And here we are able to generate their modes that is basically going to be excited at their 5.6 gigahertz, and this is basically going to be valid with respect to their actual experimental values. So here you can see your far field pattern. You can check it here. That means port 1 and port 2 is basically going to be excited into your positive Z direction, and port 3 to port 4 we are able to get into your minus Z direction. Clear? So that means here we are able to get your better correlation between your fields. Then we are going to be see your gain and radiation efficiency, as we have already know that for the in the case of your DRA, the radiation efficiency is always better than 90° or 90%. And here in the complete bandwidth, we are able to get your more than 4.5 dBi gain for your both antenna structures. Then I have calculated your ECC value based on to your far field. So you can say that the best value we are able to get it is nearly 0.25, and that is the basically based on to your far field values. But if you see clearly, the ECC value in case of your port 1 to 3 and 1 to 4, we are able to get your very good ECC value, that is nearly to less than 0.1. But in case of the ECC 1 to 2, that means if we are going to be see your antenna structure, we are going to be have the one antenna onto your top, another one into your bottom. Antenna top is going to be excited by your port 1 and port 2. Antenna bottom is going to be excited by your port 3 and port 4. So here I have plotted your ECC between the port 1 and 2 is going to be very high as compared to your port 1 to port 3 and 1 to port 4. So here you can see that in port 1 to port 2, both are going to be radiated into your positive Z direction. But due to exciting your orthogonal modes, we are able to reduce your isolation. So that ECC is basically going to be within the limit, is your 0.5. The value is less than 0.5. Further, if I am going to be put both the DRs into your back-to-back arrangement, in that condition, the DR2 is going to be excited into the minus Z direction. That means if we are going to be see your coupling between your port 1 and port 3 and port 1 and port 4, that means DR1 to DR2. In that condition, our ECC value is very, very less because the placement of DRA. And due to that, we are going to be get your complete correlation, decorrelation between their antennas. So that's why the ECC value in case of your port 1 and 3, port 1 and 4 is better as compared to their port 1 to 2 here. Now, the second structure in that condition, I have used yours just inspired with our previous structure. But what I am going to be do here, I have increased the number of ports so that I am going to be see the, as we know that if the number of elements is going to be increased, that means our system capacity is going to be increased. So what I have done here, I have increased the number of antenna elements and the ports. So here we can say that I have used your 4 antennas, that is your 4 antenna elements, 4 DR structure, and each DR is basically going to be excited by your 2 different ports. So that means here I am going to be have your 8 ports and 4 elements. So here, how to design this structure? What is the evolution process? So first I have considered your antenna 1, that is your DR1. So if this DR is basically going to be excited by your 2 different ports. The port 1 is the basically CPW based conformal, and port 2 is the basically your slot aperture. By using these 2 techniques, and both the ports is basically going to be 90° to each other, I have used this arrangement. Then I have taken this one antenna, and in the previous structure we are using the 2 elements back-to-back structure, but here I have shifted your antenna 2 from your antenna 1. Clear? So in that manner, but I have placed back-to-back, but we are going to be create some separation between these 2 antennas. So from antenna 1, I have designed your antenna 2 here, or I can say that I am using 2 antenna A and placed into your 2 different direction, that is your place 180°, so that we are able to achieve your antenna 2 or antenna B. From antenna B, I am going to be use your 2 set of your antenna B, and one antenna B is going to be placed orthogonally with respect to your second antenna B. In that condition, we are able to get your achieve antenna C. That is the basically our actual proposed antenna. So we can say that this is the 8-port MIMO antenna, or combination of their 2 antenna A, or the combination of their 4 antenna A. So here if you see, we are able to get this particular structure by using this initial antenna A. That is basically our main element, and I am putting this antenna elements into this particular arrangement to get their better ECC value or antenna performance. So now first I am going to be analyze your antenna A. So in the antenna A, as I have told that we are going to have your 2 ports, port 1 and port 2 both are orthogonal to each other. So that means we are going to be using our first technique, that is a basically orthogonal mode generation. The first port 1 is going to be have your CPW based conformal line, and port 2 is going to be have your slot aperture. And by using that, we are basically going to be get your two different excitations. So here you can see that we are going to be have there more than one antenna elements. Our first condition is true. Then we are going to be see whether both antenna is going to be share their same impedance bandwidth or not. That is also basically going to be true. And here you can see the isolation is better than -20 dB. And here you can see that we are able to generate their two orthogonal modes. Clear? So all these conditions is basically going to be fulfilled here. Now we are basically going to be see in your antenna B case when we are going to be place two antenna A into their back-to-back arrangement, but with some different distance here. So when I am going to be see, I am going to be check this performance, then I am going to be see your first S parameters. So if you are going to be see your S parameters, all the DR elements is basically going to be cover your 5.5 gigahertz band of your WLAN frequencies. And then I'm going to be see whether we are able to get their good isolation or not. So we are able to get their good isolation here. And similarly, you can see that the bottom DR is going to be excited into their negative Z direction, and top one is going to be excited into their positive Z direction. Clear? Then we are going to be have their complete antenna structure, this is antenna C or our proposed antenna structure. So here you can see that all the reflection coefficient, that means all the antenna elements is going to be share their same impedance, because we are going to be using the same antenna structure. Only we are going to be put their different placement here. And due to that, our isolation is also basically going to be there good, that is better than -20 dB. And here if you are going to be see your radiation pattern, and you can see that DR1 is going to be radiate into their positive Z direction, DR3 is going to be radiate into their positive Y direction, DR2 is going to be radiate into your -Z direction, and DR4 is going to be radiate into your -Z direction, -Y direction. So all the antenna elements are radiating into their different direction, and by using this geometry, we are able to cover almost the 360-degree angle here. So here, by placement of the DRA in such manner, I am able to improve the isolation by minimizing the correlation between the fields, and also by creating the complete coverage. So this structure is going to be create another novelty into the antenna domain. So here I have experimentally designed this antenna. You can see the fabricated structure, and then we have measured their performance. So you can see that we are going to get their better isolation than 20 dB. And here I have checked their diversity performance. So ECC value in case of their S parameters, you can see that they are less than 0.01. But when we are calculating with respect to their far field parameters, the maximum value we are able to get, that is 0.2 here. So you can see that there is a large difference between your S parameter based on to their far field and based on to their port-to-port isolation. So this value based on to their far field is going to be give their better result in case of their electro-resonant antenna. Similarly, your diversity gain, we are able to get their 8.5 dB, which is close to 10. So that means we are going to get their better results. Then mean effective gain and CCL. All values are basically going to be come into the range of their practical applications. Now, the next antenna structure, here we are basically going to be use your partial reflecting surfaces to improve your isolation of their antenna elements. So in the first structure, what I have done, I have used your 4 antenna elements. So here, 2 antennas is basically going to be go onto their top side of their DR, and 2 antenna onto their bottom side DR. But both are basically going to be, both set of their DR is placed into their orthogonal to each other. So here you can see that if we are basically going to be see your isolation between your port 2 and port 3, we are going to be get your best isolation, or port 1 to port 3 or port 2 to port 4. Clear? Because all these are the basically placed orthogonal to each other and into their back-to-back arrangement. So we can say that in that condition we are able to achieve their better isolation. But if we are going to be see the isolation between their port 1 to port 2, both are placed onto their top side and face to face. Similarly, port 3 to port 4. So here, when we are going to be analyze the isolation between port 1 to port 2 and port 3 to port 3, that is not going to be there as per our expectation. So here, what we are going to be do in that condition. So you can check it here. The isolation between the port 1 to port 2 and port 3 to port 4 is basically your nearly your 10 dBm. So here it is the need to improve this isolation. But if you are going to be see your isolation between your 1 to 3, 1 to 4 or 2 to 3 and 2 to 4, that is going to be better than minus 35 because they are basically going to be orthogonal in position. That means orthogonal mode is going to be generated. Second thing is that they are going to be radiated into their 180 degree apart. So that means there is zero correlation of the fields. And that's why we are going to get their better isolation here, better ECC value. So how we are basically going to be improve the isolation between the port 1 to port 2 and port 3 to port 4. So for that purpose, we are basically going to be use the concept of their Fabry-Perot cavity antenna. So the Fabry-Perot cavity antenna is basically going to be designed by employing your PRS structures at a certain height from the antenna elements. And this PRS is basically going to be act as a super substrate and which consists of your periodic cells along with your axis. So here you can see that we are basically going to be use this Fabry-Perot concept for two different applications. The first application is that basically when we are going to be increase the directivity or gain of their system, that means to generate their broadside wave. And second thing is that when we are basically going to be require the tilting of your wave, that means the rotation of your wave or beam steering. So here we are going to be use this particular application, that is your beam steering, so that we are able to increase the correlation, decrease the correlation between their antenna radiated field. So here, when we are going to be achieve their broadside, that means when the unit cell of the PRS are identical, in that condition, the wave emanating from them combines with the same phase and directional beam is basically going to be formed. So whenever you are basically going to be go for the enhancing your gain, you will go for your identical PRS structure. But when we want to your tilting in the beam, that means beam steering capability, in that condition, the gradual variation in the dimension is required. And due to that, the wave is going to be combined with certain phase differences. And due to that, the beam tilts at your same axis. So here you can see that when we are not going to be have your PRS, we will get your broadside beam. When we're going to put the PRS, we are going to be your tilted beam concept. So here we are going to be use this particular concept to get your isolation. So for that purpose, I have designed one unit cell. So here you can see that on the top side, we are going to be have the copper on the bottom side. That means one is the basically slot, another one is the basically your patch. So we can say that in that manner, we are basically going to be get your two different things. So one is the basically going to be formed, that is a slot base is going to be formed your capacitive grading, and top is going to be formed your inductive grading. So we can say that in the PRS, we are going to be have their two different concepts. One is the inductive grid, second one is the capacitive grid. So here our task is that we have to manipulate the phase. That means either you can change your inductance of the inductive grid or capacitance of the capacitive grid. You are able to manipulate your phase, or you can change both, or you can change any one. It is totally depending upon their designer which part they are basically going to be considered here. So in here, I am going to be you can check the top side. We are going to be have those same dimensions. So that means I am not going to be change your any capacitive structure. I am focusing on to their inductive structure, and that is basically your gradual decrease into your size. It means we are able to get your beam tilting here. So you can see that here first we are going to be have your DR1, and we are exciting into your, in that condition we are able to get your radiation into your positive Z direction. But when I am going to put the PRS, in that condition, you can see that the wave is going to be tilted from their broadside direction by the amount of their 35 degree. So by using this gradual increase into their size, we are able to manipulate their phase of their beam, so that we are able to shift that beam from their broadside direction. Now, that is a basically proposed structure. So here I have used the two consecutive structure of your PRS1. So you can see that is the center position. So from the center position, you can see that the the sizes of the unit cell is going to be increased, size of the unit cell is going to be increased. Why I'm going to be use this structure? Because we are going to be put onto your two antennas which is placed face to face. So that means when we don't have your PRS, both antenna is going to be excited into their positive direction. So you have to design your PRS in such a manner, if this antenna is going to be tilted the beam into this side, then this antenna must be going to be tilted the beam into this side. If it is not going to be tilted the beam into this side, in that condition, what will happen? For if you are going to be going to the same stream, then this beam is going to be excited into this direction. In that condition, there is no field separation. We are not able to get there any isolation improvement. What we are going to be do? We have to design this structure in such a manner so that that antenna is going to be deflect the beam into their particular axis, not into with respect to your DR1, so that the correlation between their field is basically going to be better, so that our isolation is going to be improved. So here you can see that is the condition when we don't have any PRS structure, so that DR1 or DR2 is going to be radiated into the positive z direction, DR3 and DR4 into the bottom z direction. But when we are going to be place your DRA, that is your PRS, then you can see that is your minus 35 degree in this way and minus 35 degree into this way. So that means here you can see the full correlation is going to be minimized. Your ECC's value is going to be drastically improved. So when we have done it, then we check your PRS structure, then you can see it here. When we don't have any PRS, the isolation between your port 1 and port 2 is 13 dB. Similarly, port 3 to port 4 is 13 dB. But when we include your PRS, we are able to enhance your isolation by your just double. That means 13 to 26 dB. So that is basically a better result in case of your PRS structure. Similarly, we can see that the next structure, that is your multi-band MIMO structure. So here what I have done, I have used your 3 set of your DRAs, and all these DRAs is going to be have their same dielectric constant and same diameter, but they are going to be have their different height. So by controlling your height, I am going to be energize these 3 DRA that is going to be cover 3 different band of their 5 gigahertz. So for that purpose, I have designed so you can see that here we are able to get your 3 different band with your 3 set of your DRAs. So here I am going to be use your similar concept, but in place of your triangular structure, here I have used your ring or here I have the circular structure. So you can see that here this is the first PRS for your first set of your DRA. Then this is the second PRS for your second set of the DRA, and this is the third PRS. So for each and every one, the dimensions of your patch is different because the operating frequency is going to be different. So how you are basically going to be design it, that is totally depending upon to your operating frequency and how you are able to control the phase, whether you are going to be choose your inductive grid or capacitive grid. So all these things basically you have to manage according to your tilt angle here. So you can see that here, if you see we are able to get the gradual change into your reflection coefficient and phase. Now, if you see here, that is basically our actual structure. So when we are going to be place your DR, then you can see that we are able to get your deflection or beam tilting into your all the 3 cases, and that is basically our target. So here we are able to improve the isolation more than 13 dB in the case of your second structure. So as a conclusion, I can say that I have presented here 4 different antennas. So design 1 and 2 is going to be based on to your orientation of the DRA and the generation of their orthogonal modes. And here we are able to get their 4 specially separated radiation pattern, and that is basically going to be give their multi-directional pattern diversity. And here we are able to get their more numbers of their independent channel. In the design 3rd and 4th, you can see that we are able to achieve their better MIMO performance by using their PRS structures. And here we are able to also achieve their 4 radiation beam into their different direction. But here the problem is that we required additional structures, that is your PRS additional structures, and the placement of your PRS is required your high precision. So we can say that the design 1 and 2 is going to be required, that does not require any additional structures, and also the performance is going to be there at par with their design 3 and 4. So here you can see where we are going to be required your tilting beam concept, and then you can go for your PRS structure. Otherwise, the orientation of DRA along with the orthogonal mode generation is going to give you better results. So if you see about your feature scope, then you can see that the full-fledged MIMO technology is coming for your millimeter waves. So for the millimeter waves, we can say that the DRA is going to be your potential candidate. So to design your DRAs for your 5G millimeter wave frequencies is basically the potential area to get your research there. Or we are going to be focused on your designing of your compact DRAs for your portable devices into your current situations. And third one is that how we are able to improve the ECC. So you have to focus on more techniques or the combination of your more than one technique so that you are able to get your better values of your ECC. So these are the references, and thank you. Now, if you have any question, then let me know.
Thank you, Professor. The first query is if we scale down the frequency from like millimeter waves to gigahertz to megahertz range, what will be the design challenges in DRA?
That is the good question here. Here, if you see about your DRAs fundamental, then you know that the resonant frequency of the DRA is going to be the function of its dielectric constant, its shape and size. Okay, that means the dimensions. So here, if you are going to be shift from the top to bottom, in that condition, what will happen? The dielectric constant is going to be drastically reduced from millimeter wave to your megahertz. In that condition, each and everything of the DRA is going to be changed. Clear? So if we are basically going to be doing this manner, then you have to optimize your structure in the same dimensions with same phase and with the same dielectric constant. That means you are going to be make your, I can say that your scaling factor is not going to be the same in each and every case. You have to optimize it.
Okay. What's the difference between antenna array and MIMO antenna?
That I have already explained if you see in the requirement case. So if you are basically going to be go for your antenna array, we are going to be use your more than one antenna element that is basically going to be energized by your single port. But here we require more than one ports. Port is going to be more than one. Element can be one, but port is going to be more than one.
Okay. The last query from participant side. Is there any criteria for selecting the size of ground plane for dielectric resonator antennas?
That is, if we are going to be see my experience in journal, if you are going to be go for your simulation, then normally what I am going to be prefer, I am going to be apply the radiation boundary, that is your size of your ground plane, more than 10 times of your DR geometry. So in that we can say that that is going to be your almost going to be give your infinite ground plane concept.
Yeah. Okay. With this, if any further query is left from the participant, they may directly contact to the speaker, or they may pass on their query to me, and later on I will forward the query to the speaker. With this, thank you, Professor Gangwar, for delivering a very informative contents. In the continuation, we will get another opportunity tomorrow to listen you, I think, in second lecture for third day of this event. Okay. Thank you very much once again, and thank you all the participants too. Have a nice good morning, good afternoon, as well as good night for all of you. Okay, bye. See you tomorrow at 7 p.m. as per our Indian Standard Time. Bye. Okay, sir. Thank you once again.
Very much. Okay. Good night.
Okay, sir. Bye. Good night.